I just wanted to ask if there are any presenters here that joined the call early for help with any technical setup.
Hey, Catherine, this is Mitch. Yeah, I wanted to at least screen share, see if I can get one of my, because I hope to have time to do a small demo and want to test the screen share.
Okay, yeah, we've got time for that. So if you want to go ahead and share your screen. Also, if you have any slides with sound, you have to choose sharing sound as well as sharing screen.
Okay, thank you. Good thing for me, I'm not very audio inclined, so. So Catherine, can you confirm you're seeing my screen?
Yes, I see a Simulink diagram.
Simulink, okay. Very good. That's all I wanted to make sure. Thank you.
Hey, Catherine, can you give me advice on how to pronounce Sarah Issaoun's last name?
I don't actually know. I'm sorry about that.
Okay, thanks anyway.
All right, let's get started. I'm going to go over a few logistics details, and then Jonathan is going to give an overview of Casper talk. So welcome to the Casper 2021 workshop. This is our first virtual workshop, and we have 180 registered participants. I definitely miss seeing everyone in person, and I hope the open, welcoming spirit of Casper can make up for some of the distance. I know it's harder to connect online, but please make the extra effort to connect with each other. We have a Slack channel that you can use to continue conversations from the talks or to start new conversations. And Casper aims to foster an open collaboration where everyone feels comfortable and welcome. And so we expect everyone to abide by the code of conduct that we have posted on the website. If you see ways that we could do better, please don't hesitate to let someone on the organizing committee or the advisory board know. The program is posted on the website. Each day is a mix of 10-minute submitted talks, 30-minute invited talks, and hour-long focused discussions. The session that's labeled Sparkler later today is a series of 2-minute talks that's in place of a poster session. Unfortunately, we couldn't do the usual tutorial sessions with hardware in person because we're on Zoom, but we do have 2 special tutorials at the end of the program, Tuesday and Wednesday. And speakers, we'd like to ask that you please attend the whole session for your talk if possible, so that we can reorder talks in the event that another speaker in your session has an internet connection drop in the middle of their talk. We would like to go on to the next talk and then come back at the end of the session. And I also wanted to note that the Zoom session is open early at the beginning of the day if you need any help setting up for your presentation or you want to practice sharing your screen. I'd like everyone to give a big thanks to Melissa Soriano and Ryan Lee, who are making sure that Zoom goes smoothly and that the conference is recorded. And also thank you, Ryan, for all your work on the website. And I also want to thank everyone else on the organizing committee, Francois Kopp, Dan Wertheimer, Amish Patel, and Jonathan Crouch. And we're spread across many time zones. And so if the timing doesn't work for you to watch some sessions live, it will all be recorded and posted to the website. If you don't want your presentation recorded, that's okay, but please let me know as soon as possible because by default, everything goes on the website. And now Jonathan Koch will give a Casper overview.
Okay, thanks very much, Catherine. So good morning, everyone, or afternoon, depending on where you are. This talk might be a little bit dry, but the idea behind it is that I just wanted to give a quick overview to everybody about where Casper is and where we're going, because obviously there are a lot of questions about that on the mailing list or generally as people come up. So for those who are joining us for the first time, Casper is the collaboration for astronomy, signal processing, and electronics research. We build hardware, firmware, and software. So, hardware, we've supported our own or we support commercial boards. Firmware, we have libraries and reference designs for FPGAs for building correlators, beamformers, etc., so that we can get through them quite quickly. And on the software side, we have Casper FPGA, which is our FPGA communication package to allow you to communicate to FPGAs from computers, as well as various high-speed data processing pipelines and things like that. Most importantly, in Casper, we have the people. So, Casper is a pretty large collaboration these days, and we keep in contact in a few ways. So there's the email list, which is our traditional, communication. I hope everybody is on it. There is Slack, which I hope everybody has joined for this meeting, which has various channels for all the different parts of Casper that we can talk about. We try and run these workshops about once a year so that everybody can come together and talk about what they're doing and people can find out what code they might want to be using. And there is the Casper Wiki, which is a running joke that it needs more documentation than it has, no matter how much we put on it. So if you are starting out in Casper, for example, and you find there's information you're looking for that you can't find, please let us know and either add it yourself or we can add it and working with you so that we can try and keep filling in that documentation black hole. This is a slide I stole from Dan Wertheimer. It has, it's a few years old now, I believe, and I think that it has about a third of Casper. So this sort of gives you an idea of how we're spread around the world. If you are not on this slide and you think you should be, please let me know. I would love to update it and have sort of a more accurate list of where everybody in Casper is at the moment. The founding principles behind Casper, which we try and move to keep going is sort of that it was all about rapid development and that everything was open source. So, you know, we have our firmware libraries that enable you to build a spectrometer very quickly, for example, and those libraries are open source. And as people modify them, those modifications make it back into the library as well, so that, you know, that development cycle can continue. So the idea is, you know, help your fellow Casperites. So we have, you know, reusable gateware. So we have, you know, YALO blocks, which is your 1 gig YALO block, which will work on various different platforms that has a consistent interface and those sorts of things. That we connect everything via Ethernet. The idea behind this was simply that Ethernet wasn't going to go anywhere. So we thought it was a fairly stable protocol to invest a little bit in. So if everything's connected via Ethernet, then you can update part of your design as connected via Ethernet without having to upgrade all your hardware necessarily. It's all very modular. And you know, we generally use switches to do that internet, either between FPGA to FPGA or GPUs or computers. And I have to put in this quote from Dan here: switches are free, because I think in my last system, the switches were the most expensive part of the system. But I think the idea is that as your system gets larger, the cost of the switches goes down. So it's possible to interconnect everything. Where is all of this? So it's on Git. Hopefully everybody's familiar with the Casper GitHub account, but that's where everything is. The main library is this devel.git. We're currently set in 2018 MATLAB and 2019.1 Vivado. The reason for this, and the reason these updates happen slowly, is that between different versions of MATLAB and Vivado, parameters change, or a variable becomes a protected keyword or something like that. And so it's very difficult to just shift the whole library from one version to the next. So we typically do this on sort of a 2-year type timescale. This is happening, but the current version is 2018 MATLAB, 2019.1 Vivado. In line with the rest of GitHub, as people will have seen, the master branch will be changing to main. When that happens, if you have a local version, you might have to tweak a couple of your parameters to update that. When I do that, I will also be aiming to update MATLAB to 2019.8. Vivado will stay at 2019.1. That's planned for the very near future, in the next few weeks. For general updates, a more ambitious update to 2021 and 2028 MATLAB, just for compatibility with the UltraScale Plus chips, etc. That will happen on the SOAP text branch, and that will be happening over the next few months, but hopefully that will be complete before the end of the year. And the most recent documentation these days is the Read the Docs. So there's information on the Casper toolflow, Casper FPGA outcomes platform, the tutorials, how to set things up. All of that can be found on the Read the Docs. If you find a mistake in there because, you know, Ubuntu updated something and suddenly something's incompatible, please let us know and we'll update it as quickly as possible. Where are we on hardware? So officially supported in the 2018A repo. We have the Roach 2 board, which is deprecated, but there is a branch. You can still do development on that if you want to, even though the hardware is hard to get to. We have the Snap board, which is here on the upper left. Great board for sort of large number of input, low bandwidth systems. It has 3 inbuilt ADCs that can be run in single gigabit, dual 500 megabit, dual 500 megasample seconds, or quad 250. The Scarab board below that, on the left there, is the board run by Soraya, mostly used by Soraya, of course. It's a slightly larger FPGA. You can have sort of multiple different combinations of quad 40 gig cards, or, you know, multiple 4 gigasample per second ADC cards. Red Tire is our intro board. That's for people to get started. It's a nice cheap board if you can't afford any of the others. And will allow you to sort of run through the tool flow and see how it all works, or do a very low bandwidth type spectrometer system. And then we have various ADCs that are in that can still be used via ZDock. So the Snap board, for example, still has a ZDock connector, and it is set up to work with the ADC 5G card if you wanted to run a larger bandwidth through the Snap board for some reason. We found a few years ago that it is very hard for us to develop our own hardware and still continue to support all of it at the same time. So we moved more towards a model of supporting commercial hardware as it comes out. If you have a board or new hardware that you would like to bring into Casper, the idea is that we try and run every year, though obviously it's been very difficult in the last couple, to run a hardware porting workshop where you can bring your hardware, or you can come with remote access to your hardware or something like that. And we will help you port your board to Casper so that it's fully supported by Casper, and you can, you have YALO blocks for the board, and then you can drop in the rest of your the firmware in between. Now, obviously, a lot of development has been going on along these sort of supporting commercial boards. So these are the unofficially supported, not officially supported in the current tool flow, though hopefully as we merge in the next few weeks in the 2019 A MATLAB branch, all of this will become officially supported. But at the moment, these are the main unsupported boards that I'm aware of. And if you have others to add to the list, send out a message on Slack so people know. Or similarly, have the SnapTube board out of the Institute of Automation in China, the VCU 118 Xilinx dev board, the 128 Xilinx dev board. They're both UltraScale Plus boards. The RFSoC boards, the ZCU 111, 208, and 216 are unofficially supported as well. And then recently, on the high end of ADCs, Rick Profanti developed the this 16 gig sample per second 4-bit ADC board, which is plugs into the VCU 128 or any FMC Plus connector actually, though it's supported on the VCU 128 at the moment for sort of wide bandwidth systems. And there is a 100 gig core that is semi-supported now in a yellow block fashion in Casper as well. So where you can go to get these until they're merged, the real-time radio systems GitHub run by Jack Hickish has the 100 gig core. It also has the Snap2 and actually support for some of the HTG boards as well that are at high-tech global boards that are out there at the moment as well as the Snap2. Wei Lu, who did some work when he was at Berkeley, has support on his branch for the ZCU 111, as well as the ADC 16G board. The yellow box for that are in his branches. And Mitch Burnett, who will be talking in a couple of talks from BYU, has support for the ZCU 111, 208, and 216 on his branch as well. So if you're interested in those boards and you need them before the merge happens into an official Casper, this is where you can go and get them. In terms of software, you will need their specific Casper FPGA branches as well for a lot of the communication with those new boards. Some new functionality had to be added for some of those, all listed here. Casper FPGA has been stuck in Python 2.7 for a very long time. We are working to move that to Python 3. The Python 3 branch broadly works. I would recommend the real-time radio one for sort of if you just wanted to go out and use Python 3 and see how it goes for the moment. That should work out of the box with Ubuntu 18. The main Py3 branch, however, does not work with the Snapboard right now, mainly just because you can use it for communication, but it will not calibrate the onboard ADC 16s. There is a fix for this. The merge is pending. We should get it in soon. So Casper FPGA will hopefully be moving up to Python 3 in the near future officially as well. Finally, it's been planned for a while now, but one of the difficulties with Casper for new users is actually just installing everything. No matter how hard we work to make that easier, versions change, things become incompatible, and that becomes difficult. So we've been trying to set up some workspaces in the cloud so people can log in through a VNC or similar and run a session. Thanks to the Pacific Research Platform, this may actually now happen. There's a talk by John Graham on Wednesday. If you're interested in exploring, running Casper on a cloud system, I encourage you to see that talk and talk to either myself or John beforehand, either on the Slack channel, PRP Cloud that I've created. You can also sign up for the PRP Matrix channel. If you would like to be part of that, we're going to try and run a tutorial on Wednesday afternoon. If you'd like to be part of that tutorial, please let us know and we'll set up anything we need to set up beforehand. So that is the state of where everything is in Casper as far as I'm aware. I hope it was informative, and I'll hand back to our session chair now to move on with the rest of the conference. Thank you.
Thanks, Jonathan. If you have questions for Jonathan, I think if you don't mind, just put them in the chat session and Jonathan or maybe others can help answer those questions.
Yeah, thanks, Aaron. I should have said, I'm also on the Casper Slack. If you post questions in the chat
Right
there, we can answer them all.
I think Catherine just mentioned it. If you just have questions in general, please post them on chat. And if we have questions after each talk, I will try to ask the speaker some of these questions. Before we get started, I just want to thank Catherine, who organized this meeting and brought us all together. I really appreciate her work. So we're extremely fortunate to have Sarah Issaoun to talk about. She's an expert on black holes, and in particular on the black hole at the center of our galaxy, Sag star. And she and her collaborators used Casper instrumentation to make the very first images of black holes. And I think she's going to tell us all about that. Thank you, Sarah.
Thank you very much. So it seems screen sharing is not possible. Could that be enabled?
Hey, Sarah, try again.
Okay, there we go. Thank you. All right, thank you very much for inviting me to talk about our project. It's really exciting. I'll try to spend a lot of time on the instrument and then give some context on science. Of course, I'm a member of the EHT, so everything I say is on behalf of our amazing collaboration, which is very diverse. And we have, telescope staff and engineers and scientists working on lots of different aspects of the project. So first off, why do we care about imaging a black hole? Why is this important? So first of all, black holes are mathematical occurrences of the theory of general relativity, and they also exist as astrophysical objects, which is quite amazing. They are very extreme environments where time and space come to a halt, and physics is at its most extreme. On top of that, we believe that supermassive black holes reside in the centers of most large galaxies, and they eject these streams of matter, which we call jets. These jets pierce entire galaxies into galaxy neighborhoods, sometimes thousands of light years in length, and they're the most energetic and powerful process in our universe, but we don't really know why that happens. We think the central engine is the supermassive black hole. We think magnetic fields and pressure and gas forces play a role, but we don't really understand what is the mechanism that causes these. So in order to understand, where this comes from, we need to look at the central engine, which is a supermassive black hole. We have two supermassive black holes big enough to image from Earth, the one at the center of our galaxy, Sagittarius A star, and the one in the galaxy M87. M87 you can see in the corner here. It is over here. It has a well-known jet. It is actually the first astrophysical jet ever observed by humanity. It was observed in 1918 with the Lowell Observatory in optical, and they saw this stream of matter coming from this tiny point, which is the galaxy itself. And in fact, what powers it is the supermassive black hole. So if we look up the night sky in the Virgo constellation, there is a galaxy called Virgo A, or M87, 55 million light years away from us. Because there is a lot of gas and dust between us and the center of the galaxy, we need to observe in radio waves. Although this stream of matter, this stream of plasma is visible in the optical and radio, only radio can peer all the way down to the center because it's not absorbed by gas and dust. So if we use radio waves at higher and higher frequency with larger and larger instruments to increase our resolution, we can zoom down, follow this stream of matter all the way down to its core, which is where we observe with the EHT, the black hole M87. And with the EHT, we observe at a frequency of 230 gigahertz, which is the frequency high enough so that we can peer through all the way down to the black hole. And also it just happens to be the frequency that gives us a resolution that lets us image the shadow. Now, in order to piece together a synthesized Earth-sized instrument, we use a technique called very long baseline interferometry. So I'll explain a little bit how this works. So say we have a source very far away, so that if we are in the far field regime of radiation, because it's far away, the waves that arrive on Earth are plane waves. Because of the Earth's geometry or curvature, there is a time delay between the arrival of a specific wave at each telescope. Now, the distances between telescopes tell us information about the image. Telescopes close together tell us about information on large scales because they see a lot of signal in common. And telescopes further apart see smaller signal in common, so they see a small scale structure in the image. So by combining many different telescopes at different locations on Earth and at different distances from each other, we can piece together different directions, orientations, and scales in our image and combine them. So this time difference is, however, quite important because we want to be able to correlate the signal received at each telescope. So in order to see what signal is in common, we need to time tag our data. And we do this using atomic clocks called masers. They're hydrogen maser transitions that time tag our data with very precise time. And these clocks are so precise, they lose about a second every 100 million years. Now, once our data packets are time tagged, they're recorded onto hard disks. We essentially freeze the light received at each telescope and record them and then combine them at a later time where we can then align the signals and reconstruct an image. So the EHT project is a 10-year project. The first multi-baseline, multi-telescope observation was done in 2007. Then as we expanded the array, we've added more and more telescopes, and some telescopes got decommissioned, so we lost them as well. And then finally, in 2017, we made our famous observations. In 2017, we had 8 telescopes at 6 different locations, 6 single dishes, and 2 phased arrays. Now you'll notice all of these telescopes look very different from each other. This is because we did not build them. They were built for completely different signs, so self-standing signs. And we just happened to borrow them because they can observe at 230 gigahertz, the frequency at which we need to get to M87. And they are at high enough and dry enough places and at the right places where we can reconstruct an image from different scales. So high and dry places, some of the most dry deserts on the planet, is extremely crucial for our observations. Because we're observing at such a high frequency, we are very susceptible to water vapor and turbulence in the atmosphere between us and space. And the Earth's atmosphere scrambles our signal and absorbs it because of the water vapor. So we really need to pick the right sites that maximize our signal. And our signal is very weak. So our black hole image has a total flux density of about 0.6 Jansky, so almost half a Jansky. And if you take into account all of the radio observations made in the history of humanity, it is less energy contained in that than a single snowflake dropping to the ground. So we're looking at really, really small signal, and it is really crucial that we build sensitivity. So building sensitivity with the EHT means increasing a recording bandwidth and frequency bandwidth. So across many years of our radio observations, we had different systems. The ones that matter the most is our current system here with the Roach 2 digital backend and the Mark 6 recorders. So our 2017 observations recorded at 32 gigabits per second. So this is following, the law of doubling bandwidth, which is quite amazing that we're able to see this biannual doubling with our own observations and equipment. So we observed at 32 gigabits per second with 2 polarizations and 2 gigahertz basebands. So 2 polarizations because we want to make polarization maps of the magnetic fields around the black hole, and I'll show a little bit of that later. Since then, we are now at 64 gigabits per second, so we've doubled our frequency bandwidth as well to make more polarization and frequency studies. So the signal we receive at the telescopes is, of course, an analog signal, and it's 230 gigahertz, so it's very high frequency. We down convert it to a 2 gigahertz baseband with block down converters, and then we digitize it with our Roach 2 digital backends with 2-bit sampling. And then they're recorded onto our Mark 6 recorders. This is one example of one Mark 6 unit. There's 4 boxes here, which we call modules. These Mark 6s, one records at 16 gigabits per second. We need 4 Mark 6 recorders to record at 32 gigabits per second with 2 polarizations. So there's 4 modules per Mark 6, and each Mark 6 contains each module contains 8 helium-filled hard drives, which you can see stacked here. All our Mark 6 recorders are equipped with custom cooling for high altitude use. All our equipment needs to be heavily tested at high altitude in these kind of pressure chambers, because at sites we're at least 10,000 feet above ground, sometimes 15, 16,000 feet. So we definitely do not want equipment to overheat. Also, including our equipment is not well exercised. We only observe about 2 to 3 times a year, including our dress rehearsals where we practice observing. So we really need to make sure all our equipment can easily start up and not run into too many issues when we do observe. So this is what one full backend looks like. This is from Spain. And you can see here are 4 Mark 6 recorders. We have our digital backends here, our digitizers, our down converters. And for the total of our 2017 campaign, we used 92 individual modules or 736 hard drives. In total, we recorded about 3.5 petabytes of data across our 5 triggered days. So we observe for a 12-day window during our EHT campaign, 5 days to trigger for observations, and we need to keep a very close eye on the weather. As I mentioned, we have stations at very high and dry places, but that doesn't guarantee best weather all the time, especially in April, when we observe, it's kind of marginal weather everywhere. So we need to look for these pockets of good weather for half the Earth, which is really difficult, a really difficult task to coordinate. And we were really lucky because in 2017, we had probably the best weather we've ever had, and I don't think we'll ever have this kind of weather again. So we keep a very close eye on current and forecasted weather and telescope operations to figure out when to trigger. So here are some nice pictures from our 2017 observations. On top of having operational local staff at the telescopes, we also send our own EHT members to the telescope. Here are some pictures of our EHT members with local staff. And they act as our local experts for backend equipment and for the telescopes. Then once we record the data, they get shipped to our correlation facilities, these 2 places, MIT Haystack Observatory and the Max Planck Institute for Radio Astronomy. Each facility correlates about half the data. So at correlation, we combine the signals from each telescope, we align them, we throw away all the noise that is telescope specific, only to keep the signal seen in common between pairs of telescopes. And it takes into account the Earth's curvature and these timing effects that we measure from our equipment. One thing that it doesn't take into account is, again, the atmosphere. And atmospheric effects, because we have this jitter in our phases in the data, it prevents long averaging. So if we average turbulent data, we end up destroying our signal instead of piling up and building signal to noise. So we need further data calibration. The advantage, though, is that we record at very high bandwidth. And so we do have the signal to noise to actually track atmospheric changes in the data. So from that, we can refine corrections from correlation and remove the effects of the atmosphere. So here's an example. So this is real data from EHT. So in yellow, you can see amplitudes, and in blue, phases from 3 baselines or 3 pairs of telescopes. Now, because we expect the phases from the source to vary very slowly, these few second phases, so this is over time over 400 seconds, these few second phases changes are entirely due to the local atmosphere. And so if we look at these 3 baselines, these are 3 pairs of total of 3 stations. We can actually triangulate which changes actually happen at each station. And because ALMA is the most powerful radio astronomy observatory in the world, and it brings amazing sensitivity, the baselines to ALMA allow us to have amazing signal to noise to actually track atmospheric phases on second scales and actually remove them. So once we remove them, this is what the phases look like. So now if we average down over our entire scan over a few minutes, we build sensitivity. We don't destroy signal anymore. And this is all real data. This is really what it looks like. And it's really amazing because of our high recording bandwidth, we're able to build enough sensitivity to track and remove effects of the atmosphere and really build our data, build our signal to noise, and build confidence in our data. Now, of course, understanding the data is one step, but understanding telescopes is another. We need to understand how our telescopes work, what are their sensitivities, so that our detections, which are now at signal to noise, go into a flux density scale. So we need them in Jansky so that we can make an intensity map. So in order to do that, we need to take into account, again, the sensitivity from the atmosphere, the size of the dish, different surface elevation effects, signal chain, noise level, and also polarization leakage. Now, I mentioned that our total intensity image was about half a Jansky. The polarization signal is even less than that, way less than that. And so polarization leakage is very important to remove because it creates false signal in polarization, and we really need to remove it very accurately in order to make polarization maps. But there's a trick to it. So we decouple leakage and source signal using the Earth's rotation. So because we observe for such a long time, one observing track is about 8 to 9 hours, each telescope sees the source move in an arc on the sky. So the signal from the source, the real polarization signal, is expected to move over time, but the instrumental contribution from the telescope stays put on the ground. So if we combine each arc from the telescopes, we can separate those contributions. So our entire data path from the raw signals, which is 3.5 petabytes, all the way down to an image, which just can be sent on your phone, is about 12 orders of magnitude in data reduction. And the most powerful data reduction actually happens at the calibration stage. So now that we have our final data, we can start imaging. And we use, again, the Earth's rotation with a technique called aperture synthesis. So because our telescopes are at set location on Earth, as the Earth rotates, we're sampling different parts of our image. So the Earth's rotation helps us build our virtual mirror, which you can see here. So our coverage is in Fourier space. So we're sampling different frequencies in our image. So as M87 becomes visible, we get different pairs of telescopes that give us different tracks on our coverage. And as we pile these data in time and in space, we can see how our image improves. So you can see here how as we build up our data and our coverage, the image takes shape. So we imaged M87 with 3 different softwares. This one was a traditional technique for historical VLBI. These 2 were designed for EHT specific issues dealing with systematics from our high sensitivity and our sparse coverage that we have. And all 3 gave very good answers. We tested all of these softwares against synthetic data where we knew the ground truth to make sure that we picked the right optimal parameters for our software. And this is the final result. So these are the 3 software images for April 11 observation. And in fact, the famous image I'm sure you've seen of the black hole is simply the average of these 3. So that is the first image of a black hole. But during our 2017 campaign, we triggered 5 observing days. 4 of them had M87. So we have 4 individual observations of this ring. This one was April 11, and here are the other 3. So as you can see, over our 4 days, we don't see significant changes. Every single day gives us a ring the same size, brighter on the bottom with a dark spot in the center where the black hole shadow is. In polarization, which we just released a couple of months ago, we get these beautiful images. So on top of our total intensity ring, we added the information from polarized light. You can see that polarized light only lights up the southwest part of the ring and gives us this kind of spiral structure in the polarization angles. So we get a spiral polarization structure across our 4 days, and it looks pretty similar across the days as well. I'll explain everything that we learned from this. First, we measured the size of our black hole, which was 42 microseconds on the sky, which is because we know the distance of the black hole, we were able to measure the mass, which is 6.5 billion solar masses. M87 is one of the largest and most massive black holes in our known universe. I really love this comic because it actually shows us the scale of this image. Although it's 42 microseconds, it's the size of seeing an orange on the surface of the moon with your naked eye. It is actually bigger than our solar system. So you can see the sun at the center, Pluto, the orbit of Pluto around, and Voyager 1, which is the furthest human-made object that we've sent out, just at the edge of the shadow. Now, the next step is to understand what exactly we're looking at. So we've imaged it. We know it's a ring. We know it has a shadow. What does it tell us about the physics? What are we learning? So in order to do that, we simulate a black hole and its environment. So we use fancy simulations that take into account the space-time around the black hole with general relativity and the physics around it. So we have matter orbiting, falling into a black hole, which we call the accretion disk. And it also spews out these jets of plasma. And then these disks and jets are also threaded with magnetic fields, which help push in and out material. and there's a black hole at the center. And then because of the very hot gas temperature, the gas is not atoms, it's ions and electrons. And so because we have electrons, magnetic fields, if we have very fast moving electrons spiraling around magnetic field lines, they emit synchrotron radiation that is polarized, and that is the emitted light that we observe with the EHT. From different types of physics that we try to understand, we made a simulation library. So this is our total intensity simulation library to try to understand the signatures of a ring. There are lots of different ones here that have different, gas properties, magnetic field properties, but they all have something very clearly in common. They all have a dark patch at the center and a bright ring around it. So why is that? Why do they all show the same thing? It's because this signature in our main image is a direct effect of gravitational lensing. Because we have such a strong pull from the gravity of the black hole, we have light rays from around the black hole that get bent by the gravity of the black hole. And as seen from a distant observer, if you have a lot of light rays, which is the case with the gas around the black hole, as a distant observer, you will see this kind of puffed up shadow surrounded by a ring of light. And that's exactly what we observe. Now, you'll also notice that our ring of light is not smoothly uniform. It has a part that is brighter on the bottom. The reason of that is because of the inclination we're looking at. We're seeing a full ring. We're looking almost straight down the barrel of the black hole. And one side is brighter than the other because of Doppler boosting. So the side that is brighter is coming towards us and the fainter side is going away from us. So another thing we learned from our simulations is also that the gas rotation around the black hole orbits clockwise and that the spin of the black hole is pointing into the board, into the screen. Then we also looked at polarization simulations. So we have our polarization images. We want to understand what did the magnetic fields look like and whether they actually play a role in launching this famous jet that we see in M87. So we made polarization simulations, which you can see on the left with perfect resolution, and on the right, what we would see with the EHT. And we compared these polarization maps. So what it teaches us is that if you have a black hole with an accretion disk with threaded magnetic fields, if you have weak magnetic fields, they would kind of look like concentric circles, the field lines. And then the synchrotron radiation that would come from these field lines would look like spokes on a wheel as seen from Earth. So we'd make polarization maps that would look like, that stick out like this, just like the animation. Now, if you have a very strong magnetic field, you will get the opposite effect. You will get spokes on a wheel, magnetic field lines, and then the synchrotron radiation would look like concentric circles as seen from Earth. So this is what our image would look like. But as you remember, our polarization image looks like a spiral, right? And so it means it's kind of in between weak and strong. So if we have a spiral structure of the magnetic field, the synchrotron radiation that we see from the black hole is also a spiral. And so we learned from this that the magnetic field strength around the black hole is about 4 to 30 Gauss. And it has a spiral structure that has a vertical component. The interesting thing about the vertical component is that it means it's able to push gas out, which means that it could be the cause and the direct link between the black hole, this magnetic field, and the jet launching. So that is where we stand now with EH2 results. So what's next for us? We've added new stations since then. We just observed in 2021 with the added Greenland telescope, Cape Peak telescope, and Noema array. We're hoping to add a telescope in Africa, but we're thinking about really long term as well, which is the next generation EHT. So with the next generation EHT, we'd like to have, because now we have the sensitivity from our large dishes, like ALMA and like Noema. So we'd like to put small dishes at lots and lots of different places on Earth to fill our coverage. So we're no longer sensitivity limited. And what's really cool is that, say if we have a simulation here of a black hole and its jet, what we would see with 2017 is, just the dominating ring that we see in our images, but we know this jet exists, and we don't yet have the sensitivity and coverage to be able to image it. But with the NGHT, we'd be able to make images and link directly the ring to the jet emission from the black hole. And this will really help us understand how the jet behaves and how it connects to the black hole. And we want to extend to space. We'd like to have longer baselines, so no longer limited by the size of the Earth. We'd like to have faster orbiting in low Earth orbit to fill our coverage and go to higher frequencies. Even if we have an entirely space-based array, we're no longer limited by the Earth's atmosphere, so we can go to like 1 terahertz and observe. But next generation EHT means next generation challenges. This is my final slide. Just to think about where we're going, because we're adding so many more telescopes, we need to look at our monitoring and control development. We can't just keep sending telescope experts to sites, especially if we want to observe more often. We're going to have a lot of data, so we want to expand from our 64 gigabits per second to 256 gigabits per second. We need to think about data storage and real-time correlation. For a ground-based array antenna design, we need to look at smaller dishes, which should be sufficient given the current sensitivity. For a space-based array, we're looking at whether we have a single orbiter with our ground array, which allows for quick filling, or an entirely multiple orbiter system, which allows for very slow filling, but very sharp images. Then we want to build sensitivity in space. If we want a wide bandwidth and large data rates, how do we get the data down? We can't just keep hard drives there, and we can't send an airplane to get it. So we need to think about how to downlink this kind of data. And also timing in space. So our major clocks that we have at the sites are the size of a mini fridge, and we can't really afford to put a mini fridge into space. So we need to think about compact solution for timing, which is really crucial for our signal for VLBI. So I'll stop here. Thank you very much, and I'll take questions.
Thanks, Sarah. That was great. Andre Gunz asks, why are the signals correlated at 2 different locations, US and Germany?
The reason for that, I guess there's 2 reasons. First, we have a large amount of data, and our correlation facilities don't just work on EHT, they also work on other projects, and mainly geodetic science. So antennas on Earth that try to learn about the Earth's surface. So not a lot of their time can be spent on EHT. So it was more cost efficient for us to split the work. And it was also better as well for us to cross-check correlation. So as I've told, we like doing things multiple ways. So we do our data calibration with 3 pipelines, imaging with 3 pipelines, polarization with 5 pipelines. So we like to be completely sure that we're doing things the right way. So doing correlation in 2 different sites allows us also to cross-check the correlation output, which we did do. We had a set which we called the golden scans, which we picked from each correlator's data stack. And then those were sent to the other correlator and correlated in the same way. And then the outputs were checked to make sure that the correlation was happening in the right way for both sites. So it is also an additional layer of cross-check.
Great. And James Smith is asking about why the Roach 2 boards were selected for EHT. He points out that often VLBI is done with this off-the-shelf DBBC, and was that also suitable for EHT?
So I think now we're using DBBC3 at 2 sites, at Apex and at Pico Veleta in Spain. I think the easiest way was to use the Roach 2 at first, because it was, I guess, more easily transportable, because they're much smaller than the full units. And we had, I think, VLBI equipment units at each telescope already, and it didn't make sense to buy kind of a full new DBBC3 unit rather than just update parts of the equipment. I think that's why.
Thanks. We have one more question from Adita Tamar. what about EHT's capabilities to measure the spin of M87? You measure the mass, but
Yeah. Yeah, so we couldn't really measure the spin. What we could tell from our total intensity observations and polarization observations is that a Schwarzschild black hole, so non-spinning, is ruled out. But we don't know exactly what the spin value is. I think with more observations, especially looking at time variability, there we'd expect to learn more about spin. So time variability is different depending on the black hole spin. Yeah.
great. Perfect timing. Thank you so much. Great,
Thank you very
great talk.
much.
Thanks for starting off the Casper workshop. I just got a really cool talk. A lot of people are thanking you on chat. Next, we're lucky to have Mitch Burnett. Mitch is the Casper expert on RFSoC, and Mitch has been doing a lot of great work porting a lot of RFSoC boards to the Casper tool flow, and he's also been helping all the Casperites figure out how to use RFSoC boards and chips. Mitch, take it away, please.
Yeah, thank you, Dan. Those are kind words. All right, I should be sharing screen. If anything goes wrong, somebody, Dan, speak up, yell at me.
Can you make it full screen for us?
Oh, yep. There we go. So again, first, I'd like to thank the local organizing committee, Catherine and Dan and everybody involved. It's good to be with you despite the circumstances. I hope everybody continues to stay and be well. And so with a lot to cover, I think I'll just jump right in. So as Dan mentioned, I've been working with RFSoC. I'm a program and project engineer at Brigham Young University for our Alpaca project, an L-band phased array feed. And so we're using the RFSoC, and by necessity need to know more about it. And so I'll be just giving a brief overview of the RFSoC for those of you who may not know much about it, are interested, know it exists, but want to know a little bit more about what it can do, especially in these applications for radio science. And then I'll kind of dive into what the work I've done to support them and where we're at, where we're going. And if time permits, a little just small brief demo showing how everything fits together and the ease of use. And so the UltraScale Plus, all of my figures and plots, I note if they come from Xilinx, that way you can just go yourself and get and look at these similar images. And so the product guide 269 for the RFSoC is where a lot of these helpful figures come from. And so the RFSoC is a recently new, I guess 3 years now by Xilinx. They have 3 generations of the chip, and it integrates alongside the programmable logic, a processor system, the A53, along with multi-gigabit transceivers, and then what makes it the RFSoC, the integrated A to D and DAC with digital down and up conversion, all within a single package with varying capabilities. And again, I could have shown the large Xilinx product selection guide, but that's kind of a lot to digest. So I've kind of condensed it to the RFSoCs that I'll be speaking to and kind of the ones that are more geared to some of our applications. If you want to go full specs, I encourage you to look at their product guide. But so now we have 2 generations by this point that we kind of are targeting, Gen 1 and Gen 3. The difference primarily being in the sample rate of these parts. So the Gen 1 28DR, which would be the ZC111, has a 4 gigasample sample rate, can accept 8 ADCs inputs, each with their own digital down conversion. Then the 29DR is a 16 input board, sampling at 2 gigasamples per second. Then the Gen 3 kind of ups those by adding about 500 gigasamples per second to each. The ADCs have a resolution from 12 to 14, depending on the year, with varying decimation and interpolation values. And then, as we can see at the bottom, the PL resources, they have a modest amount of DSP slices, which make it, for Casper, particularly an interesting board to continue to perpetuate this idea of rapid development for test of instruments, both small scale to large scale, as a small channelizer or just something that can capture and forward data through Ethernet switches. Sadly, there is only 200G CMAX, so that does kind of limit the total Ethernet output, but it's still a very capable platform, combining multiple RFSoCs together. And Xilinx does have in their datasheet the ADC performance, datasheet 926, most current version being 1.8, and they report all the parameters that we care about when looking about analyzing if this will fit our application. I've just highlighted briefly noise spectral density, which is fairly good, averaging from -145 to 150 dBm or dB full scale per hertz. And so I also encourage you to go there if you want to know more about how these ADCs perform. And then, as I mentioned, there's kind of two flavors of the RF ADC architecture. They're all built and laid out similarly. There's 4 tiles. Within each tile, there's 4 ADCs, but between the 2.8 and the 3.8, or the 2.9 and the 4.9, they interleave the ADCs to achieve the higher sample rate of the 2.8 and 4.8. And so in the 4 ADCs, that's what they call it, a quad RF ADC tile. And then in the dual RF ADC, they call that just a dual tile, where they've taken an extra pair of those ADCs, interleaved them yet again to achieve the higher sample rate. And then the RF signal path is very typical of what you would see, but just now condensed inside the integrated package. The ADC followed by a series of RF signal path, but most notably is that these RFDCs are capable of digital down conversion with accepting both a real signal right off the antenna, providing it a complex baseband IQ, or reel-to-reel sampling, or if you have a premix stage, bringing in IQ samples and continuing to sample IQ using, and then being able to do gain and phase QMC calibration on that, and then continue using decimation if you were. And then on the Gen 3, the only difference really, besides the improved or more decimation capabilities, is that they now have a digital step attenuator on the front end. And the other notable thing that I wanted to at least bring up is that in Gen 3, they now have this concept of tile clock forwarding. On Gen 1, you would bring the external clock inputs into each tile, and you would have to condition those clocks separately per tile. But now the one tile can receive an input, and shown by the green paths, forward a clock to the adjacent tiles, and it can forward the sample clock, or it can forward a reference clock, or it can forward the output of the internal PLLs that are within each tile. And so that lends to a lot of flexibility in terms of board layout, or different requirements in terms of conditioning on your sampling. Different layouts do affect the quality, the noise measurements of your ADC, but going and looking, say, at datasheet 926, it isn't incredibly drastic, so much that these capabilities all provide a lot of flexibility. And so, as I mentioned, different possibilities here: sample clock forwarding, reference clock forwarding, the reference clock being what you would provide to the internal PLL that would then be the sample clock for the ADCs, or you can span them across different tiles. And then the one question I actually get asked the most about is, what is the clocking network layout and the capabilities of multi-tile synchronizations? Because for beamformer applications like my own, for Alpaca or correlator systems, synchronization and the deterministic repeatability of these systems is a very big deal. We don't want to have to spend a ton of time calibrating each time. And so I thought this was one of the big ones that I would dump more information to help the audience here. And so there's really 4 main clock signals. I've highlighted them with the red arrow on the right. the PL clock, which is our user data clock that's clocking the user logic, the PL sysref, and the analog sysref. These are the sysref in the similar sense to JESD204B. Xilinx has taken that standard, augmented it a bit, but they're sysref in that sense, if you're familiar with the standard. And then the sampling clocks for the A to D and DAC. And so going through, I've used MTS. It's very capable. It works. Just some things to know and how the procedure works, things to know that the MTS synchronization is only specified in their data sheet to be accurate within ±1 sample period. However, this is primarily dependent on PCB clock phase alignments at the chip inputs. And so for boards, eval boards out there, ZCU111, 208, 216, high-tech global boards, I've used MTS and they're all good on these boards, getting very good synchronization. And so that's more things to be aware of if you're laying out your own board. And in essence, how they do the synchronization procedure is that the sysref for the analog clock is first captured with the sample clock and used to scan a delay tap chain of 128. They take the period, break it into 128 smaller periods, and they scan for a safe sampling position where the analog sysref is in the center of the sample clock period. Once that is determined, a synchronous reset is issued, and the tiles come out of reset and they're effectively synchronized. All the digital components of them are. And then the last in the sampling themselves. And then the other digital component to synchronize is the output FIFOs, which again is done by comparing a time of flight difference between the analog sysref and the PL sysref, inserting a marker bit into the FIFOs, watching when that marker bit comes out, comparing and then setting the read counters delayed to match the outputs. And so the real kick with and catch with the aligning the FIFOs is that the analog sysref and the PL sysref need to be phase aligned on the input of the chip. And again, that's primarily a PCB layout, but if it doesn't work, it's usually because there's a problem with the board or problem with phase alignment of these signals. And so as an example on the ZCU111, if an example of MTS, we take 8 inputs, all continuous wave, and then applying MTS, now we see on the right that they come out synchronized. As I mentioned, these are deterministic in the sense that from startup to startup, you can apply MTS, and as long as the phase relationships on the boards of these clocking signals do not change, then startup to startup, you'll have the same synchronous behavior. You could extend MTS even further to do both deterministic and sample alignment. So if you not only need startup to startup, the samples coming out in the same deterministic order, but also that they are sample aligned, that can also be done within the framework Xilinx has provided, just requires noodling through some of the APIs and data sheets. And so again, a lot of the questions I get are on clocking. This is taken from the ZCU111, but most of the RFSoCs that I've worked with, that I've seen, use something similar. They have a 2-stage onboard RFPLL net that I call an RFPLL network, where they have a dual loop LMK clock generator for jitter clean, phase noise cleaning that can either accept an external reference or just use an onboard TCXO. Provided these provide clocks to the RFSoC, but before then is an LMX that could provide either the sample clock or again a low frequency reference that are yet to be used inside the RFSoC in each tile's PLL. And so there's a lot of clocking capabilities and flexibility. And then one of the things is that with Gen 3 RFSoCs using sample clock forwarding, it can even simplify the layout of RFSoC boards, or just the clocking in general, the extent to what you have to do to configure and bring up the sampling on the board. And so without further delay, I guess, I hope the moment we've all been waiting for is, so what do we have inside Casper? And so over the last, I guess it's been a while. So I first started about 2 years ago at the first Casper RFSoC, or Casper hardware porting workshop that I went to. And since then, between all of the things, trying to learn the tool flow, now, the last few months, I've really kind of hit the road trying to bring these RFSoCs into the platform, into the tool flow. And so these are the ones that I'm working with. I've worked with a little bit, and I'm trying to support. We have primarily the Xilinx eval boards, and then the High-Tech Global, what I call the ZRF16. I think that's how they market it as well. That's from High-Tech Global. And then you'll see the PYNQ 2x2, or I think Xilinx would rather call the RFSoC 2x2. But that's the small Xilinx University program board accepting 2 inputs of the A to D, 2 outputs on a DAC. And each of these platforms, they have varying level support. I'm primarily carrying the ZCU216 and the ZRF through and testing those, and then I'm advancing the other platforms along the way. But now I have the entire framework in place, and so bringing all the others up to speed should be pretty straightforward and easy, and I'll cover that more later in the roadmap. But if you haven't seen one of these boards, here they are, the ZCU111 on the left, the PYNQ RFSoC 2x2, ZCU216, and then the High-Tech Global, the ZRF16. There's 2 revisions of that board, a 29DR with Gen 1 part, and then the 49DR that has a Gen 3 part. And then I had to use one for the ZC208 because I had a brief moment to use a 208, tested a little bit on it, but then I lost access to it. And so what does using one of these platforms look like in Casper? Well, it's just like any of our other platforms. Now we've just kind of added a little bit more information to help bootstrap the RFSoC. And so you come in, you select your platform. In the case of the ZRF16, 2 flavors of options, you would select that. Then the user clock rate. This is, again, the clock rate you're going to do your DSP at. And then because there's a lot of work to do to bring up the RFPLL, under the hood, I've made it easy to specify what the input PL clock is on coming from your RFPLLs, to use that to create the IP user clock and to support multi-tile synchronization. And then the real kind of kicker, what really makes this work, is the RFDC yellow block. Without the ADC yellow block, there really is no RFSoC. And this is what I've been primarily working on. And I aim to achieve the same flexibility of the RFDC as you would in Vivado by abstracting some of the computer engineering hardware type things that would have to go on in understanding it. And so you can select and enable the different tiles and a section for the sample clock and all clocking configurations, and then really going through and customizing the ADC performance. Like I said, try to make all of the flexibility of the RFSoC there, and so it supports real to digital output, reel to reel, reel to IQ. If you already have a mixed signal, IQ to IQ, can set the decimation mode for adjusting the achieved processing bandwidth and the number of parallel samples. You can grab whatever you want to achieve either the full output sample rate of the part, as shown in this one here, 8 parallel samples. I guess I have a destination by 2, but I have one later for the full one. But really, I'm trying to say that very capable platform to target and work with. And then the difference between the dual and quad, under the hood, the RFDC yellow block can identify which part you're working with and validate your input based on, oh, I have a dual tile, I know how to set that up. Oh, I have a quad tile, I know how to validate and present to you how to configure it. And so that's great, but so who's using it? Well, by necessity, I'm using it in our Alpaca, and I hope a lot of you will hopefully like to start using this. But Alpaca, joint collaboration between ourselves, BYU and Cornell. It was to be a facility instrument to Arecibo, but unfortunately, the recent collapse and demise of Arecibo has caused us to try and transition with a hopeful switch to GBT. But 138 element path, cryogenically cooled, and we're using a heterogeneous GPU FPGA backend connected by Ethernet switches with a Zoom spectrometer where we have coarse channels in an oversampled PFB at the first stage, and then do second stage GPU beamformer correlator spectral line transient processing. But for the RFSoC, how would you configure my application in the RFSoC? Well, I have 12 ZCUs requiring multi-tile, multi-board sync. I enable that. I want all the inputs. I enable all the tiles. I enable all the ADCs. And then also we're doing direct sampling at L-band, 2 gigasamples, targeting second Nyquist. We also want to use the digital down converter, decimate by 4, and use the NCO to frequency tune and align the center of the band inside our low pass anti-aliasing filters. And so this would be the example configuration shown on the right to do this for my application. And then this, I apologize, I put this slide in because I also wanted to appeal to the developers out there. This is probably the most dense of my slides probably, and I'm going to flow right by it. But as these boards become more capable, the MPSoC, the RFSoC, there is a more reliance on software. And so there's this hardware software interface that needs to be negotiated in the tools, so that way the user, we can maintain the Casper mentality of a quick metric time to science, and the user can design and Simulink, hit go, and out pops the bit stream that we can just program, and then our Casper software tools just work, knowing how to manage that. And so software is a big component of that, and particularly in the RFSoC, where it's very driver driven. There's a lot of low-level registers, but they're mostly labeled reserved in the data sheet, and you would have to dissect the Xilinx provided C driver to even understand how a lot of their bringing up the driver would work. So instead, we use that. But we need the Xilinx shell archive to generate these software platforms. And so to do this, we need to bring into the tool flow better ways to integrate with IP integrator and software. And so some suggested changes I've made would be we initialize the project in the init stage. This allows for the platform yellow block to continue to maintain its role as setting up the project underneath the hood and the tools. And so now Xilinx children IP and IP integrator, either the MPSoC, RFDC, or whatever Xilinx provided IP you wanted, can insert themselves, configure, and then now Xilinx IP coexists with Casper hardware inside the project. And then once we have that exported hardware platform, Jasper's exec flow, we add a next step that now starts using HSI, the hardware software interface, which is the same underlying tools, to build software platform projects. And that way we can generate device trees, bring in needed drivers, build drivers, and generate all of the hardware specific output products that the software would want to use to bring up these drivers. And then at the end of the day, we still provide our FPG that we use and to program, continuing to use TCP Borg server and Casper FPGA. So it would be similar again to Prog Remote, where now RFSoC specific functions are implemented within these software paradigms. So to kind of show that, I've taken TCP Borg server, extended it to RFSoC, so it supports the RFDC driver, can configure the RFPLLs. With the framework in place, it can now be extended to even better make use of the hardware peripherals and software peripherals. And so I'm working on updating the NCO for in-band tuning now, and then testing 100 gigabit Ethernet, so that way it can bring up the PHY clocks and then probe QSFPs. And so I've shown here the added methods. And just as an example, the RFDC driver initialize, it takes all of the hardware output products from Jasper. It will detect if it needs to apply the device tree overlay to bring in the RFDC or update any MPSoC configurations. And then for RFDC specific tasks, it kicks off the driver, and then we can run a status check to show that, yeah, indeed, the hardware was successfully applied, the driver was able to identify the RFDC, read the parameters, and that the tiles are up and running with PLLs locked. And again, one of, I think, a very flexible feature with this is to be able to apply clocking that we can bring. One of the challenges we've had is, okay, how do we provide one set of solution that works for everybody? Well, we really can't. Instead, we now have a way where we can upload and program RFPLL clocks to whatever your specification is. And so here, kind of walk through that an RFDC configured at 2 gigasamples per second, wanting to use the internal PLL with a reference clock expecting a 250 hertz megahertz clock. And so from reset, we can initialize, look at the driver, we see that the RFDC is waiting for the valid clock, the PLL is not locked. I can take an already dumped TIX hex output register file for my onboard LMK PLL, upload that, and begin to program. And that is taken by the board using I2C, programs the LMK, and we're up and running. And then, so TCP Borg server, we don't typically work with that. That's the intermediate server managing everything on the FPGA, but instead we use Casper FPGA, which, as Jonathan mentioned earlier, is our client connection that can either provide an interactive control through, say, IPython, or a scripted control for large scale operations. And I've extended adding an RFDC class using CatCP transport to command TCP Borg server to use these new methods, and then also included the low-level register memory maps if we wanted to peek, poke, and really debug any sort of problems that come in.
But Mitch, you've got a few minutes left, maybe 4, and a couple of questions. It's up. You can handle the questions in chat if you want to do the demo.
Do you think it'd be good that I run through it real quick?
Can you do the demo in 2 or 3 minutes? And
yeah,
then answer the questions in chat. Would that be okay?
Yep, it'll be real quick. So for the demo, I just wanted to bring in Casper FPGA to show, well, I guess I did also want to show just a sample design that I'll be using for the demo. Kind of some tutorial information, just the RFDC going straight into a BRAM capture. So it's just capturing time samples. And from Casper FPGA, we bring up our FPGA in the normal way. We can upload that example design. The FPGA is ready to go. And we can just ask Casper FPGAs, hey, what ADCs? Oh, look, I see my RFDC. We can bring the RFDC in, and we can call that init, which under the hood is making all that handshaking with TCP Borg server. And again, ask for the status. We see that prior to this, I had just asked somebody remotely to power cycle the board for me. It's now waiting for a sample clock after being programmed. And with a TIX output register file with a 250 hertz megahertz clock, can upload it. And prog PLL, I want to program the LMK, pass in that file, and optionally upload, because this file doesn't exist on, well, actually, show that first. RFDC, show clock files. I have 2 clock files already up there. They don't provide the configuration I want. So there, that's when we know we want to program, upload, and show that now these tiles are up and running, they're sampling, and sure enough, that clock file has been added into the list of clock files for configurations as I want to maybe bring this board in and out of different operational modes in some system. And then I can begin sampling and capturing data. So if I run those captures, average them real quick, and then I can plot that response. I again had configured at 2 gigasamples, decimate by 8. and I'm inputting 100 megahertz tone, and we have the output here. So, yep, brief demo. I know it's a flyby, sorry, but that's really I'll just throw up this last slide that shows where we're going. There's places to go. I'm bringing the tools along. That's all I wanted to show here. 100G is next. Once that's kind of solved, these platforms are really fully supported in the flow, and then it's just bringing all the other ones up to speed. I'm working on tutorials, documentation. We'll have those, and I'll leave this slide up, my last slide, and I'll take questions. Hello?
I think you're muted there, Dan.
Mitch, I'm sorry. Can you do the questions Q&A on the chat session?
Chat. Yep.
Yeah.
Certainly.
You've got some good
Well,
questions, and we'll figure out a way to capture this because I don't know if it'll get captured in the recording, but it'd be nice to capture the answers.
Sure. Thanks. Thanks again, Dan. Thanks, everyone. Sorry, such a drive-by.
Thank you, Mitch. That was great. Really important stuff. It'll change Casper in a good way. So let's see. I apologize for not getting to the questions, but I think we should move on, try to keep on schedule. Really appreciate that great talk. So our next speaker is Michael Piscopo, and Michael has been working on the using GNU radio on the Allen telescope array. Michael?
So there's been a slight switch up to the schedule. My name is Derek Kozel. I'll be presenting on GNU Radio in this 15-minute segment. Come back 1 hour from now to catch Mike Piscopo
Okay.
with his talk.
Sorry.
But I am here if you need me.
I'll be pointing people your direction for sure. So hello, folks. My name is Derek Kozel. I'm the president of the GNU Radio project. And I'll be giving a really quick overview talk that we thought would be useful for you to have before Mike Piscopo's talk comes up. I'm sorry, I'm just seeing a flickering in chat that I don't know whether I should be monitoring or not. Yes, Gren. Okay. So as I said, my name is Derek Kozel, and I'll be giving an overview talk about GNU Radio. I am, as I said, president of GNU Radio and a principal investigator at the SETI Institute and a PhD researcher at Cardiff University. So a few hats here. Only the first two are the ones I'm presenting today. So GNU Radio is an open source framework and runtime for digital signal processing applications. It's a data flow architecture, and I'll be showing you a few examples of how applications are developed with it, and hopefully leading both you and myself to be convinced that this is a really good partner application with the existing functionality of Casper's FPGA and host side processing. There exists a large library of digital signal processing blocks. The project's been going for 19 years at this point and is community run and maintained, much as Casper is, fully free and open source, same deal. And it's in use a lot by research groups, industry, academic, and government projects. So there's a very wide variety of users, and that really gives us the benefit of being tested against a lot of hardware and stressed in a lot of interesting directions. So the software is pretty robust. The main framework is usually used either as a library or as a complete application. The runtime and core of the DSP are written in C++, although increasingly we see people implementing native Python processing, offloading to FPGAs, GPUs, and other heterogeneous accelerators. We see some specific DSP chips and custom ASICs. Later on, as was hinted, there'll be two talks, one today and one tomorrow, talking much more in depth about the higher data rate and heterogeneous aspects of GNU Radio. While the core of GNU Radio is written in C++, there are higher level wrappers, and so everything is accessible from a Python environment, and there's automatic translation between these languages. This is a photo of our main graphical user interface, and it's in many ways the thing that people are familiar with if they already know GNU Radio. It actually only represents a small portion of the functionality, but it is a very useful one. This companion allows for data flow process graphs to be created entirely graphically, click and drag, select a block to change its parameters, and be very transferable. These can be copied and pasted between machines quite simply. And what this does is actually generates a full Python and or C++ application that can be used separately from the companion. These are run on embedded systems all the way up to cloud infrastructures. And on the right-hand side, we can see an example of an actual application running plotting data, in this case, a communications signal. The core functionality, we have a library of standard DSP blocks. We have data transport, so reading and writing files. This includes some of the standard file formats that I imagine the Casper community is quite a regular user of, including HDF5. Network transport, it's been tested all the way up to 40 gigabit Ethernet. I'd love the opportunity to try 100 gig. We have a built-in digital TV modulation and demodulation, perhaps not so interesting to the Casper community, but an example of a larger end-to-end pipeline. Graphical displays and controls that are continuously evolving. Much of the value of GNU Radio, however, is in the out-of-tree modules. These are third-party plugins that allow you to add in additional functionality over time. These include things like full satellite decoders. So if you are trying to test your array against GPS satellites or similar orbiting references, there are flows for that can do some interesting things around timing analysis. We have TensorFlow and other machine learning libraries, OpenCL accelerated blocks to get higher performance. Mike Piscopo is actually one of the primary authors of some of the most frequently used blocks there. And then a whole bunch of protocols that, again, may not be as interesting to this community, but perhaps for other areas of your RF experience. And then we have a directory of modules called cgram, where you can search for these out-of-tree modules. GNU Radio is free and open source, as I said. It's community built. We've had a number of official and unofficial organizations over the years. And in our current form, we are community directed and have an elected leadership. You can find out more about that on the website. I wanted to, quickly dig into the radio astronomy side of things, given the audience that we have here today. Just to name a few organizations that are already using GNU Radio as part of their astronomy pipelines. There's the Canadian Centre for Experimental Radio Astronomy, Sierra. MIT Haystack uses GNU Radio and is actually one of the main maintainers of our Anaconda installers, as I'll mention again later. They also maintain the digital RF package, which is where our HDF5 support comes from. The Duolingo telescope in the Netherlands has been doing an extensive amount of work with GNU Radio, both interferometry, downlinking satellite imagery from from probes orbiting the moon, and a variety of other applications there. And I believe they've also done some standard radio astronomy observations of hydrogen lines and other atomic lines. The Pictor Radio Telescope and the DISPRA project, two separate efforts, are both working on kind of high school or university level learning telescopes, things that you might be able to build in your backyard or as a small organization. DISPRA is a project here in the United States, and it's NSF funded to get these tools into the hands of teachers. I think this would be a really interesting opportunity to collaborate between Casper and GNU Radio and DISPRA to perhaps integrate Casper's low-cost option on the, sorry, not the Raspberry Pi. You'll probably know the board, I mean, the small
Red Battaya.
The Red Battaya, exactly so. I'd love to get my hands on one of those at some point. I know they have a new RF optimized version. Pictor is based in Greece. But in terms of the largest setup that I know of, we have the ATA demonstrator. The Allen Telescope Array, which I have a photo of on the next slide, is in Northern California and is an array of 42 dishes. We currently have an agreement and collaboration with the SETI Institute, which is actually GNU Radio's partner organization at this point. We entered into an agreement with them last fall and have been progressively developing more and more shared programs. This testbed is the first part of that, and it provides an opportunity for GNU Radio users and community to start getting into radio astronomy in a deeper way. I have a series of examples of observations and pipelines that have been set up over the last 9 months, and I know I'm already out of date, having seen the Slack messages from yesterday. This is a great opportunity for people to get access to high quality live RF data with capabilities that really just can't be replicated at home or even at a large university scale. The ATA is a great platform for developing a lot of these applications. Here we have a photo from May of 2 years ago. There was meant to be more of these hack fests, but we all know how the in-person events have gone recently. So here are 3 of the 6-meter satellite dishes of the Allen Telescope Array and a group of GNU Radio, industry, and academic individuals who came together for a hack fest. As a result of this effort, we now have this testbed launched and a lot of the code running, and we certainly hope to be holding more of these in the future. At the Allen Telescope Array, what we currently have is some commercial off-the-shelf hardware in the form of National Instruments NI USRP receivers. This is only, I understand this isn't only in terms of Casper, giving us 4 times 250 megahertz channels. We also have access to some Casper Snap receivers, and Mike Piscopo will be talking about those a bit later. And then we have a variety of other FPGA and GPU hardware. I'm conscious of my time, so I'm going to begin flying through a bit of this to make sure that we get to the end. Here's a few images of initial shakedown results. These occurred very quickly at the start of the program, and we can see an interferometry image generated in the middle. I believe that was using 11 baselines. In terms of things that may not be so possible using Casper-only pipelines, we can demodulate a lot of satellite traffic. And so here are some analysis and downlinked images from weather satellites and doing some timing analysis using Iridium satellites as a reference. We can also access the Deep Space Network and make observations there. Some of the recent pieces that have been done are high precision positioning of the Chang'e 5 probe on its way to Mars, which recently just reached Mars. In terms of current developments, this is going to be the highlight of the talk tomorrow. We're working very deeply on improving our ability to handle heterogeneous environments. Up until now, GNU Radio has primarily been a CPU-based architecture. It's handled multiple CPUs, multiple machines collaborating, but hasn't focused so much on interoperability with FPGAs and GPUs. It's been possible, but certainly not convenient. There have also been some large developments in user friendliness, and I think particularly of interest to the radio astronomy community, we have great support now in Anaconda. So whether you're on Windows, Mac, Linux, Raspberry Pi, you can install Anaconda and get GNU Radio running quite simply. And as I mentioned, we have this third-party block ecosystem with Cgren. I think I'll gloss over these. We have a library called Volk, our vector optimized library of kernels. This is a math library with SIMD acceleration. It's used extensively within GNU Radio and supports a wide variety of host CPU architectures, including a lot of the ARM variants. SIGINMEF is an alternative data standard to HDF5. We think that there's some complementary features and some nice pieces here that may emerge as being useful. Already many government groups and research groups are developing data sets, and it's become quite popular within the machine learning community for creating IQ data sets. There's a variety of tools up, but I'll let you take a look at those in your own time. For further information about the project, we have our main website, gnuradio.org, a variety of documentation and tutorials on our wiki. We also find that it's impossible to keep these as up to date and as complete as we'd like, but they have been improving dramatically over the past few years, and they are a great resource. Our annual conference, all the videos are located up on YouTube under GNU Radio Project. We also have a mailing list, the Discuss GNU Radio list, and live discussion at chat.gnuradio.org. In terms of contributing and joining, and this is where I'll wrap up, we do have initial support for the Snapboard, and we'd love to test against other Casper hardware. A particularly valuable contribution from members of the audience here would be to wrap existing radio astronomy DSP code into GNU Radio, letting us create more portable pipelines that can be easily plug and played with different hardware. We have our conference coming up in September, and it would be great to have talks from the Casper community there. And also, you're welcome to join a weekend session at the Allen Telescope Array. Just send me an email for that. Thank you very much. In 1 hour, we'll have Mike Piscopo's talk on a large correlation engine. And then tomorrow, the in-depth half-hour talk about the heterogeneous computing scheduler. I'll be in chat and look forward to answering questions there, I imagine. Thanks very much.
Thanks so much, Derek. That's really great. It's a great collaboration, and I'm super pleased to have you guys working hard to collaborate with Casper and put all these energies together. Thank you, Derek. I think if you have questions, please post them online, and hopefully Derek will get back to you. Let's move on. Our next speaker is Jenny Smith from UC Santa Barbara. Jenny's PhD is all about using these MeerKAT detectors, which are amazing things that for every photon, you get an X and Y position and a very precise time for every photon. And she's been working on the digital back ends and polyphase overlap, polyphase filter banks, and she's going to tell us all about it. Jenny?
Thanks, Dan. Okay, hopefully that's all working. You guys see my screen?
Yeah,
Good to go.
Awesome. Okay, so thanks for the introduction, Dan. As he mentioned, I'm a third-year graduate student in Ben Mazine's group at the University of California, Santa Barbara. I'll also add I just started interning at Xilinx with a PYNQ team. Patrick Lysaght will be speaking later this morning, and he'll tell you more about what PYNQ is and how it works. Today, I'm presenting my graduate work developing a high-throughput oversampled polyphase filter bank on an RFSoC. As Dan mentioned, my group works on a specialized detector called a microwave kinetic inductance detector. So one array of these detector devices is shown in the background of this image here. Unfortunately, I won't be able to go into a lot of detail about what MeerKATs are and how they work. I'm going to be focusing on the readout, which involves sending and receiving RF signals to this chip and processing them with an FPGA. Our current readout scheme uses a Casper Roach 2 board. Sorry, the Roach 2 has served us very well, but now we're working on upgrading to the ZCU 111 because effectively we're able to do more with less. So Mitch gave a really great overview of all the capabilities of the RFSoC. I also chose to make my own table instead of pull one from Xilinx, but effectively you can see with a much smaller form factor, less weight and less power, we can read out more of our detectors. And so by making the switch, we will be able to increase our ability to bring our arrays to harsher environments such as outer space, and also for ground-based experiments, we'll be able to build higher density arrays. So many of us are really excited to take advantage of these awesome new RFSoC devices, but if you sit down and go to make a high density DSP design using that full ADC rate, you'll quickly be faced with a problem summarized here. So the data coming from the ADC is sort of like Niagara Falls, which is this image shown here. And the programmable logic is more equipped to handle data in slower streams, kind of like this babbling brook image over here. So there's parallel streams that are all sort of moving much more slowly than this torrent over here. A channelizer is a really useful structure that allows you to go from Niagara Falls to babbling brook. The basic way that a channelizer works and the function that it does is it takes this large spectrum here with a very fast sample rate, and then you'll take some chunk of the spectrum that you're interested in and you'll move that to a lower frequency. So here I've just chosen to move this speckled bin to 0 Hertz. You low pass filter to get rid of all the other bins surrounding. And then once you've isolated that smaller chunk of the initial spectrum, you can safely downsample. And so this is sort of the babbling brook data over here, and you can send this off to the programmable logic to be processed. If you want to analyze the entire spectrum, you have to repeat this entire process for every single bin. And if you're not careful, that can get pretty resource intensive. So our channelizer is doing just that. We have to process a full 4 gigahertz band sampled by 2 ADCs on the ZCU111, each running at 4 gigasamples per second. This little zoom in here is showing a small portion of the band and the sort of what the spectrum looks like. So you can see these little dips here. Each one of these corresponds to one of the detectors on the array. And these are the signals that we need to channelize and process. So in this 4 gigahertz, there are 2,000 detectors total, and we need to keep 1 megahertz of bandwidth around each to actively read out the signal. And I should mention that every time we change our MKID device or the detector array chip, these frequencies move. So these are not fixed frequency locations. So there are a couple options for how you could design a channelizer to do this task. The most simple to understand is you could do a per channel approach where every single frequency that you want to down convert, you multiply, similar to the image that I showed on the previous slide, and then you'd apply a low pass filter and then you downsample. But the problem is you're doing a very expensive high speed multiply, a very expensive high speed filter, only to downsample at the end, and you throw away a bunch of those data products that you worked so hard to generate. Another sort of type of channelizer is you could do a tree structure where you continually have the spectrum, and every time that you have the bandwidth, you're able to drop the sample rate to the corresponding new Nyquist rate. So then you're not doing quite so many high-speed computations. But the most efficient thing you could do is a polyphase filter bank, and that involves moving that downsample operations ahead of all math so that you're only doing computations that you actually are going to use. So that's the magic of the polyphase filter bank technique, and I'll tell you a little bit about how that works here. So this is a really detailed graphic showing sort of the ins and outs of how the polyphase filter bank works. So here on the left, this is that low pass filter that's going to form your individual channels. And so how this works is the coefficients from this prototype low pass filter get spread out along these parallel branches here. And I've tried to show you how those coefficients get spread out. So that's the shape here. So the star, the first coefficient goes to the first row, the second square goes to the second row, the third one's a triangle, and so on. And then you repeat that process. And I really want to call attention to the fact that this downsample operation is happening here before any math happens. So the data comes in over here, it gets spread out along these parallel branches. These are just basic FIR filters. This multiply step over here is effectively doing the translation. And this is just the same as an endpoint FFT. So for anyone with a background in multi-rate DSP, this picture on the right here, this block diagram is showing exactly the same thing, but this is the traditional way that you'd represent what's happening on the left. I just like the left because it's a bit more detailed and easier to understand what's going on in these like individual blocks here. But the main takeaway if this is all Greek to you is just that there's no wasted computations when you do the polyphase filter bank technique. So unfortunately, we can't do a basic polyphase filter bank. And that's because up here you can see I've shown the response of the channelizer if you just do a standard critically sampled polyphase filter bank, which I described on the previous slide. So our detectors are going to show up somewhere in this spectrum here. And it's possible, since we don't have great control over the fabrication, that they show up directly in between two subbands. So if we had a detector that was located right here, it would be attenuated. It wouldn't show up well in either bin, and we effectively wouldn't be able to use that detector, which is unacceptable to our lab. And so we have to oversample, which has a response shown down here. So by oversampling, you're able to widen every bin. And now there's nowhere in the spectrum that the detector could show up where it wouldn't be well represented in one bin. Now, oversampling adds a lot of complication to the actual DSP, and I'm kind of trying to represent that by showing you the data movement over here on the right. So in the critically sampled case, you can kind of imagine that prototype filter is moving along the data in these sort of like unit steps, like it moves over by the whole length of the filter every time. Whereas if you oversample, it's more kind of like a moving average. So the same data samples are going into the filter multiple times. And so I've shown a specific case here of 50% oversampling. So this filter is moving over halfway each time, and each data sample here is going to be processed by 2 different coefficient sets as compared to the critically sampled case. And that allows us to widen these subbands here 2 times as wide as the critically sampled. So here is the implementation that we came up with on the ZC111 that accomplishes that oversampled polyphase filter bank. There are 4 main blocks which make up this design. There's a HLS delay and interleave block. That's Vivado HLS, was used to generate that IP designed by my lab. There's Xilinx FIRs. It's a FIR just available in Vivado. There's another custom IP block, which is another HLS block that reorders data. And then there's the SSR FFT, which is the vector FFT that you can pull out of SysGen, Xilinx system generator. So the main key here that I want to emphasize is that we were able to figure out a way to use the super highly optimized and reconfigurable Xilinx blocks to do the really compute intensive DSP portions. The real trick here was figuring out how to use HLS to sort of manage and route the stream so that the DSP actually worked out. So what's happening here, I'll just sort of note the specifications of this channelizer. The input bandwidth is 4 gigahertz. It's coming from an I-ADC and a Q-ADC, each running at 4 gigasamples per second. This delay and interleave block is how we're reusing the data. So in order to 50% oversample, every data has to go into be processed twice. And so the stream is copied and delayed with itself. And then it's fed into the Xilinx FIRs. And in order to process the data through 2 different coefficient sets, we've effectively doubled the amount of time domain multiplex channels here so that the data is processed by 2 different coefficient sets. So here, this is sort of representing an entire filter matrix, which is roughly 30,000 taps total. It's 4096 rows and 8 columns. So coming out of here is 4096 channels. They're each 2 megahertz wide and they're overlapping by 50%. Just to describe the rest of this block diagram, after the Xilinx FIRs, the data gets out of order because of oversampling. So every other frame is permuted like it does like almost a 50% rotation. And so this HLS reorder is just a ping pong buffer that reads and writes to different addresses to reorder the data in the correct natural order before going to the vector FFT. And this is there's 16 parallel data lanes here, and the whole thing is running at 512 megahertz. I've also put down the resource utilization. In this paper here, I did a more detailed comparison of the resource utilization of this channelizer and other channelizers that have been published. Unfortunately, the other channelizers that I found didn't expose the implementation in this level of detail, and they didn't make the source code available, so I couldn't build it myself and see how the internals are working. And so without that information, it's really hard to take resources and scale them to different bandwidths, because this bandwidth is much higher than any of the other published channelizers. But at least like generally viewing the resource utilization versus the bandwidth, it looks like we did pretty well in terms of resources. And I'm really proud of this 512 megahertz clock speed. Up until we completed this design, it was sort of an open question whether you could get HLS to make timing at that level. Okay, so now I want to just share with you a little bit about how we did the verification for this design. So we used the PYNQ system, which I mentioned. Patrick's going to go over that in more detail later this morning. But essentially, one of the main benefits is it gives you a Jupyter Notebook Python environment, which runs on the processor system on the board, and you're able to interact with IP in your design. And it makes it really easy to debug and generate data and view the output. So this PYNQ overlay, this is the block design in Vivado. Inside that dark blue hierarchy, that's where the oversampled polyphase filter bank design lives. And what this whole overlay is doing is essentially just allowing us to generate data in Python, fire off DMA transfers to be processed through the oversampled polyphase filter bank. And then we can read it back into that Jupyter notebook and plot it and see and make sure that it's actually doing the correct oversampled polyphase filter bank DSP. So this plot on the left was sort of one of the final verifications. This is a magnitude versus frequency. And what I did was I generated 2 different tones in Python, and I placed them so that these different channels, the different channels are color coded differently. So this is one subband that's the purple, another subband is the salmon, and another one is the teal. And I generated a frequency that would go directly in between the purple and the salmon, and then one that would be in its own bin in the teal, all with the same amplitude. And you can see the tone shows up, the one that's in between two bins shows up equally well in both bins with the same amplitude with respect to the one that's all in its own bin. So that means that the channelizer is correctly oversampling. If it was not oversampling, we would see some attenuation in this tone. And then it's always nice, I think, to view the actual area layout utilization. So this is just pulled straight from Vivado, and I've labeled the different leaf cells that are being used by the different blocks. Again, I just want to highlight the really intensive DSP operations are coming from the Xilinx blocks, so the SSR FFT and the Xilinx FIRs, and the HLS blocks are sort of used as glue to make these all work together. So finally, I just want to say that this whole work is open source. It's available under a GPL3 license. It's on GitHub. You can build the entire project. And I'd really appreciate if anyone who's interested in polyphase filter banks or oversampled polyphase filter banks gives it a try. So it's been designed to be adapted and reused. Here I've just copied a small snippet of code from one of our HLS designs. Basically the key parameters, like the number of parallel lanes, the number of samples coming out of the ADC, the end groups is something that we use to keep track. Those can just be changed with pound defined statements in the HLS, and you can regenerate this IP and sort of like reconfigure the Xilinx blocks and remake a different design with something like a different number of channels or operating on a different bandwidth. Okay, so that's all I have for you today. Thank you so much for listening, and I'd be happy to take any questions. This is a picture of my lab from pre-COVID.
Hey, thanks so much, Jenny. Let's see, you got a few questions. I'm going to ask a couple of questions. Is the readout density limited by the detector architecture or by the DSP? And also, did you have to do any manual routing or just Vivado options?
That's a great question. So the detector architecture, or the detector, like the density of the detectors, I think is currently limited by fabrication. So when we make the chips, we put a lot of them on there, but many of them are shorted or don't quite work properly. And so just by getting more expensive fabrication facilities, we can improve the detector density. The readout can handle 2,000, but typically we get about 80% of that on a good chip, is what our pixel yield will be. Oh, and the second question was about routing. So we did not have to do any sort of floor planning or placement, but what we did have to do is, especially in the HLS blocks, go in and change the pragmas and change how the streams were being routed. So a common thing we do is like, for streams that all had identical T-valid lines on the axis streams, instead of having 8 of those on 8 parallel streams that were all the same, we'd get rid of 7 of them and pack them all together. So explicitly packing the data onto wide buses in HLS allowed it to route much more efficiently. And also we just found that upgrading the tools, so re-implementing the IP in different later versions of HLS did much better timing wise. Great.
You've got another question, but I'm hoping you can take that on chat. Thank you.
Awesome.
Thank you, Jenny. Great work. Our next speaker is Arash Roshanineshat, and he's going to tell us about this wideband radio digital spectrometer. I think Arash has been working on EHT stuff and doing a lot of stuff with RFSoC as well. Arash?
Thank you, Dan. Let me share my screen. All right. Hello, everyone. My name is Arash Roshanineshat. I am a third-year PhD student at the University of Arizona, and I work with Dan Maroney and David Forbes. Today, in my talk, I'm going to talk about SWRDS, SMT wideband radio digital spectrometer. First, I'm going to give a quick background about SMT. As we saw in Sarah's presentation, SMT is one of the very first members of the EHT array. It is a 10-meter dish located at about 11,000 feet on Mount Graham in Arizona. You can see the relative location on the map on the right side. Current receiver at SMT produces bandwidth at about 4 gigahertz of IF, which is about 16 gigahertz of bandwidth. But the current backend digitizes only 2 gigahertz of it, 1/8 of the whole bandwidth. Also, the current backend is very old. For our new backend, we choose to use Xilinx's RFSoC chips. And for our development board, we use ZC111. ZC111 has 8 ADC chips on it, and we are interleaving pairs of ADCs. So since we have 8 ADCs, if we interleave pair of them, we will have 4 channels. Each ADC is clocked at 4 gigahertz. Sorry, this should be 4.096 gigahertz. This is to do that, we have designed this board was designed by David Forbes. And as I said, there are 4 input channels, and there's a shared clock at around 4 gigahertz, and 2 output DACs, digital to analog converters. Mitch, in his talk, talked about LMX and LMK. Since we are using external clocks, we are not using LMX and LMK at all. We are just bypass the internal clocks, and we are using external clocks. Here is the block diagram of this board. The channels go through filters, equalizers, attenuations, then amplifiers, and they are fed into ADCs. Also, the clock is going through a time delay chips, and they go into the clock of each tile. The interleaved tiles are tile 0 and 1, and 2 and 3. In this block diagram, I have shown the programmable parts of this board, attenuators and time delays. They are connected to shift registers, and the shift registers have an SPI interface that can be programmed. Attenuators are 6-bit, they have 6-bit control, and time delays have 5-bit control. So each bit will change each clock by the step of 3 picoseconds. So in total, we will have about 100 picoseconds of delay. We can control it. It is adjustable. On the right, you can see the board, this new board sitting on ZC111. And on the left picture, I'm showing the cables connected to 2 channels and the clock. Here you can see I have put a block diagram of my design, my PL design, FPGA design. The data from ADC comes into streams, XC streams into a sample delay IP. They go into a sequencer IP. I'm calling it sequencer because it puts the samples into the right order. And then it goes into a channelizer. The reason that I'm calling it channelizer because I want it puts 2 channels together. So in the output, I want to see 2 channels. There are 4 channels. In the output, I want to record 2 channels. Also, each IP in this design is configurable. They are configured using XI Lite. They're using the Zinc processor. PetaLinux is running on Zinc. Actually, we have talked about PetaLinux a lot in Casper Slack. As I got used to PetaLinux, I actually find it very pleasing to work with. Here you can see the design in Vivado 2020.2. Currently, it is the latest version. But let's talk about the software. As I said, the PetaLinux is running on this on the Zinc processor. Massive amount of code is running both on the ARM processor on the ZC111 and on the server. In this slide, you can see the block diagram of the software running on ZC111. What I have done, this code is written in C++. I have created a core, I call it HOP, and then I added different modules to it. There are calibrators, I have added FFTW3 to do FFT on the board. There's a peripheral manager. This peripheral manager, so my design has the ability to read the config files like of the PL design. So in the future, if I add an IP to my design, it's very easy to introduce it to my code on the ZC111. It is very easy to add new IP, remove IP, add interrupts. The network manager, the network is connected to the server through, they communicate with each other through JSON packets. So the packets are transmitted in JSON format. And here is the design. This code is running on a server. Interestingly, these two ZC111 and the server are communicating through Ethernet. So I can put my ZC111 on the mountain, and then you run this code in the lab here, right next to me, or it can run on Raspberry Pi. The main of the server is written in Python. I have created a Flask API, and I'm writing a web interface for it so that people can command, run, or change the configuration on the board using their browser. Any relatively new browser can run the web user interface. Also, I'm using my favorite game engine called Godot to write mobile and desktop user interface for my design. So the application can run either on Android, on your phone, or on your Apple iOS devices. Here is a very quick sample of how it looks like. There is like on the left side, you can see I have issued connect command. I can select the channel, run the calibration, and record. On the right side, you can see the calibration output. I have just put a small amount of it, how it looks like when the logger logs the messages. But let's look at some results. In this slide, I show you the output when I turn on ZC111 and I hit the record. You can see the input is 250 megahertz. There's a big spur on the right, on the higher, there's a big image spur on the right side, and the time domain looks very distorted and bad. So we need to do calibration. We set the synthesizer, the signal generator, to a noun frequency, let's say 250, as it was before, and then I run. I put the calibration command, or I push the calibration button, and I get this. You can see the sine wave is a lot cleaner, and the spur on the right side has gone low, very low, about like negative 60, about 60 dB difference. The calibration process calibrates the offset, amplitude, and time delay. As I said, time delay is adjustable, and amplitude are attenuated on the board that are adjustable, and the offset is also adjustable through Xilinx's QMC. But those are tools that we can use to calibrate. I use to calibrate my device, my signal, my interleaving ADC interleaving. And 250 is just arbitrary. I calibrated the device with 250 megahertz, and then I increased the frequency. The image spur grew, and like as you can see for different frequency. To go to higher frequencies, to frequencies higher than Nyquist threshold, I had to change the synthesizer. This is why it is not locked to a reference frequency. This is why it's not on the center of the frequency bin. But for this slide, the peaks were more of an interest to me. As you can see, the peaks get up to the spur get up to negative 20 dB, which is very far more than this spur here, which I calibrated the design, the interleaving. But for astronomical applications, this is not a big of a significance. However, I really want to, in this project, I really want to get as perfect interleaving output as I can. You might ask, have you tried calibrating on higher frequencies? The answer is yes. when I calibrated on, let's say about 3.2 gigahertz, the SPUR goes away. However, the SPUR shows up at 3.7 gigahertz. When I calibrated at 3.7 gigahertz, the SPUR goes away, the image SPUR, but it again shows up on 3.2 gigahertz. This is one of the challenges or issues that I'm working on right now. For the future plans, I want to really finish the GUI, the web application, and the desktop and mobile applications, and like user interfaces. I want users to be able to do everything or monitor the device with their phone or using their browser. Also, as I said, I'm investigating why the SPURs get larger for different frequencies than the frequency that I calibrated in. Also, in the future, right now the FFT is done with software, but we are going to implement FFT on the FPGA. So the FFT is gonna happen on the board and not on CPU. Also, we are going to have PFBs. PFB, Jen had a great talk about PFBs. We will use PFBs in our design in the future as well. That was my talk. Thank you so much. I'll take any questions now.
Thanks, Arash. Yeah, Rohit Miguel asks, do you use the SD card to run Petalinux as embedded code?
Okay, I am not using SD cards. So what I'm doing is I use a network file system. So I put everything on the like a shared folder. I boot U-boot through JTAG, and then I tell U-boot where to get the Petalinux files. So U-boot will download Petalinux and load it on the fly. I am not using any SD cards.
Okay, this has to be a quick answer, or maybe you can answer offline, but Kaj asked, he thinks it looks like you're doing this purely in Vivado, and could you be using the Casper ADC LO blocks and other Casper blocks?
That's a very good question. So one thing about my design is that I'm using, when I started this project, I had to use the latest software because Vivado had provided the tools that I needed in their latest version of their Vivado. This latest version was not supported by Casper back then. So I had to use Vivado by like Vivado. So I just started using Vivado for their features, and I kept using Vivado. But in the future, yes, it is definitely possible to use Casper tool flow as well. But again, because of the tools that I needed at the time that I started the project, it wasn't available in Casper. Mitch is working on it. Tyrone is working on it. In the as we go, there's more tools to be implemented with Casper toolchain and Simulink.
Great. Okay, thanks so much, Arash, and thanks to all the speakers. A lot of wonderful talks and a great launch to this workshop. And so I think we're just 2 or 3 minutes behind schedule, but we'll take it out of the break and we'll start on time at 30 minutes after the hour will be the next talk. But before you go, I'm wondering if the organizers have any announcements that they want to make. Any, Catherine or anybody, are we good to take a break? Okay. Catherine?
Yes, we're good. And I'm going to post a message in the chat about a way to sign a Get Well card for Adam Isaacson.
Okay.
That'll be in.
Thanks everybody for great talks. See you in 12 minutes.
Hey, Ryan. Tyrone's just gonna test out his screen sharing for a second. That's okay.
Okay, sure thing. Go ahead.
Okay, thanks.
Is Wiz around?
Can you let me know if you see that, Amish?
Yep.
Okay, great stuff. Thank you.
Cool. Thanks, Ryan.
Yeah, no worries.
Hey folks, this is Mike. I think I'll at least get my presentation up here. There we go. Get some video on. You guys can see my great background. Yeah, folks, I guess we're up at the top of the hour. Should I go ahead and get
It's just
started?
it's just about to ask the same thing. If Catherine, Dan, you're down with
Yes.
it, should
Yes, Amish, you're chairing this one, I think. So get started as soon as you're ready.
yeah, well, I think Mike's even more ready than I am. Next speaker for the starting of the next session, Mike Piscopo, as Derek, I think it was alluded to almost an hour ago. I was actually trying to dig some dirt on Mike, and I watched his presentation at GRCon in 2019. So as with most people here, he's a pretty cool dude. And take it away, Mike.
Thanks, Mitch. Yeah, so hi, everybody. My name's Mike Piscopo. For those of you who don't know me, I've been working with the GNU radio community for probably about 8 or 9 years now on various pieces. And as Derek mentioned, I've got a number of out-of-tree modules in support of the GNU radio community, including some of the GPU accelerated components that we work with. But just to kind of jump in a little bit, I can give you a little bit of a background on where some of this work that we'll be talking about came from. But as Derek mentioned earlier, GNU Radio and the SETI community and the Allen Telescope Array have gone into this community partnership, which has really been fantastic. I know from the GNU Radio side, and I hope for the Telescope Array side as well. But there's a lot of talent out there in the open source GNU Radio community that yeah, they may do the signals processing and radio astronomy by day, but sort of on the quote unquote amateur or outside their business time, do all kinds of signal processing work for the open source community and GNU Radio and work on a number of projects. So I think when the opportunity came up to work with the Allen Telescope Array a few years back in the 2019 hackathon, a lot of folks jumped at it. And given the whole COVID side of things, this whole 2021, as Derek mentioned, we did a virtual one back in September. But it's been great because there's on the weekends, there's generally about 4 antennas. The GNU radio community is very familiar with some of the EDIS USRP or USRP radios, and there's 2 of their N series at the Telescope Array to support whatever science or experiments the GNU radio community wants to do. So there's been everything from work I've been doing with Whale and Daniel Estevez on getting the correlator work done, to tracking various spacecrafts and updating TLEs. It's been, I guess, a really exciting kind of 8 or 9 months. But on my side, I had done the original correlator interface back in 2019, I guess it was. And over the past year, the ATA has upgraded a number of those old systems to bring in the new snaps, and that correlator went away. And so at the hackathon this past year, it kind of came up, well, hey, you did the old block. Do you want to take a shot at it and get the new snaps in there? So I said, sure. And as we got into it, realized that the correlator had went away in the mix of all that. And I thought it'd be kind of a interesting continuation of work to pick up and see what we could do about getting a correlator integrated that would work within the GNU radio framework as well. So right now there's about 21 antennas slated over the course of the year to be online at the Allen Telescope Array with the new snaps. Right now we've got about 12 of them that are actually online. But it's an interesting use case. I mean, here we have 42 antennas. And the use case unfolded as, could we come up with a framework that worked within GNU Radio where we could have many, non-limited number of antennas within that structure, even multiple groupings running simultaneously with different antenna pods, and running multiple correlator instances, potentially with completely different parameters, and possibly running on the same NUMA multi-CPU system at the same time. Using GNU Radio within the framework of the ATA. Sounded like a worthy challenge to me, so I didn't realize it was going to be about 8 or 9 months worth of work and continuing. But just to kind of give you a little bit of an overview, this is what the pipeline at the ATA looks like today. We've got the dishes feeding into snaps that handle the F-engine pieces. They do the PFBs and the channelizing. Each of them has 2 10 gig Ethernet interfaces that feed the data out over an Ethernet network in UDP packet formats. And then there's various levels of maturity in the X engine pieces. We've got some that still have 40 gig interfaces, but the idea is to upgrade them to 100 gig Ethernet interfaces when we can get the whole array online. And then obviously some high-speed disk I/O for data storage. But right now we're working with about 1 gigahertz of bandwidth, and the snaps can divide that up into 2048 channels, dual polarization per antenna. So every 256 channel block is about 1 gig of data on the wire. It's 4-bit packed IQ data. So that kind of gives us a little bit of a metric to do some off-the-cuff math in terms of what the overall bandwidth looks like. So, trying to get to this next milestone of 21 antennas with 256 channels to start, we're looking at about 21 gigs of traffic on the wire. And ultimately, if we can get to all 2048 channels, we're looking at about 168 gigs a second, which is quite a lot of data when you've got a general purpose CPU and box sitting somewhere in the mix of all that. But we've been making some pretty good progress. So current state, we've done live observations with 12 of the antennas with 256 channels in real time. And I'll talk a little bit more about that. And based on the timing that we've got with our current X engine, looks like they could support about 22 antennas on the NVIDIA 2080 cards right now, but we've got a roadmap for more. There's just time limited in terms of the number of things that I know we still need to kind of get in to get that performance up. And I think we'll probably get, another 4x-ish or so based on architecture before we even start to look at the 3090s, I think. And right now the testing in terms of more antennas is really limited by the antennas with the new snaps. But I think there's a few more that are looking to come online sooner than later. So just to give you a little bit kind of an overview of what we're doing within the GNU Radio community, and Derek showed the companion or the UI where we do the building of the various flow graphs, and we kind of like to talk in terms of blocks. But to support this overall structure, what we've put together are 3 specific blocks. One is the snap source that actually takes the data from the network in the snap 2.0 format and handles, which is just what you'd expect with network traffic. So it handles multi-packet frame reassembly, error detection. What do we do with drop packets? How do we backfill so that the data streams stay time synchronized? It can do one of 2 things. It can either leave it in the packed 4-bit format to pass it straight along down to the GPU, or it can do the unpacking and put it out in 8-bit format, which is kind of interesting because then for the rest of the GNU Radio community, the snap source just becomes an FFT'd data stream that they can do any kind of signal processing that they'd like downstream with it. One I'm not showing here is we've even got a reference antenna correlator that's GPU enabled as well. But it doesn't have to feed an X engine. As I mentioned, you can do whatever you want with it. But to support some of the multi-antenna operations, there is a standalone synchronizer block, and the goal of this is really just to make sure that all of the streams get time synchronized across the antennas and stay time synchronized for whatever the next downstream task will be. In the context of the correlator that we're working on, that functionality is actually baked in, which saves us a good bit of overhead with some memory moves, and we don't have to worry about that. But the goal on this X engine that is probably a little bit different than most of you might be familiar with XGPU is that the GNU Radio community likes flexibility and being able to run in different environments, right? So this one's based on OpenCL, so we've got support, natively out of the box for it to run on NVIDIA or AMD or Intel hardware. It's not necessarily locked into any metric on the number of antennas, and it doesn't have to be a multiple of 2 or 4 or 8. So if you wanted to go with 3 antennas or 5 antennas or 17 antennas, you could do that. The kernels are all dynamically generated at runtime based on the parameters. So you could run multiple copies of this on the same box and tie them into different NUMA nodes if you wanted to, and they could have completely different parameters set up. So it does handle all of this throughput in real time. And XGPU was sort of the framework that I started to look at when we started to put all this together. So the output to disk format is exactly the same with that. It's that lower triangular format, if you guys are familiar with XGPU, just to make compatibility much easier. And then we've got some post-processing that we do. And Daniel Estevez has been incredibly helpful, kind of taking over that while I've been focusing on the correlator part of it. But you can see there the image that Derek had put up earlier was from one of our tests with the 12 antenna. But we handle all of the delay calculations and the phasings and the UV fits conversion in some post processing that Daniel has available in one of his Git repositories. So just to kind of show you how simple this can be with GNU Radio, those blocks you see on the left are really all it takes to link up the antennas in the snap source and run them through the correlator. And I've got a command line tool that we put together where you don't even need to build this in the UI. You can do it all at launch time on the command line and say, I want these 5 antennas or these 14 antennas, and it'll handle creating all this flow graph kind of stuff for you within the code before it launches. But you can see that the top picture there was one that we did where we only had 5 antennas online. And as we started to mature, we got down to the 12 antenna side of things. Obviously, as more antennas come online, we'll continue to test and tune. But it's been a really interesting thing. You can kind of see the evolution in here in terms of how we've done with performance. And the yellow curve that you see in there was one where it was XGPU as my baseline, basically with its 32-bit float. I tried a couple different settings on it when I was originally doing some testing just to see where the performance flushed out. And I know there's some other newer 4-bit versions and such, but this seemed like a pretty good baseline to start with my comparisons on. And the red line there was actually our 80 millisecond real-time floor. So whatever we needed to do as we were adding antennas, we needed to try to stay below that, or we'd start to blow our real-time frame. So you can kind of see how it's evolved over time as we started to make some changes, like making sure we passed in the 4-bit directly to the GPU and let some of the unpacking happen there. We found that the way that the GPUs were handling cache hits, that reordering the matrix on the GPU really helped optimize some of the throughputs as we went to do the correlation phases, and then capitalizing on some of the new architectures where the memory reads can actually happen in 256-bit blocks. So we've been working all these optimizations in, and right now, obviously, we're projecting we can do about 23 antennas. And I know there's a few more things like some overlapped I/O that we're not doing yet, and some other tricks in terms of chunking it into different time pipes to get better cache optimization. I think is going to get us where we want to be before we even start to look at the 3090s that are going to very quickly double the memory throughput. So just, one of the things that we've been shooting for with both of these has obviously been flexibility. So from the radio astronomy perspective, this X engine block doesn't necessarily need to be tied to the snaps in particular. You can use it with any inputs within GNU Radio that can feed it the FFT vectors. So it's not tied to snaps. If we want to use the usurps or anything else, once we get that format, you can just feed it in and take it from there. No restrictions. I did set it up to support both single and dual polarization, because I know sometimes, especially with the usurps, we may only be feeding in one polarization for that. So I wanted to try to get that flexibility captured in there. OpenCL was something, again, to try to get as much support. Anything that supports OpenCL kernels, this code will run on. So it may not necessarily even just be limited to the GPUs. If there's other hardware that you've got that's OpenCL compatible, you could run that correlator on there without having to make any additional code changes. And as I mentioned, we optimized in the synchronizer, but it's based on the timestamps that come downstream to handle that synchronization. And the same thing with the snap and the synchronizer blocks. So you can take that output as an F engine and feed it into whatever you want. If you don't want to do correlation, but you want to do something else with the data, you don't even necessarily need to leave it in that 4-bit mode. The block can automatically be told to go ahead and do the unpacking and pass that down the stream. And GNU Radio has a number of other blocks built in to do other format conversions. So if you want to go to like signed 16-bit integers or floating complex, you could do that as well. And yeah, that really kind of opens up the possibility to do whatever signal processing you want downstream with the feeds from the antennas, which I think makes the array highly configurable and kind of open to whatever you can imagine you want to do with the dishes. All right, I kept it to 15 minutes, guys. I did it. I guess now's a good time to open it up for any questions anybody has.
That was very cool. I mean, not to say that there weren't too many questions in the chat. Catherine was asking about the source that was imaged, but I think certainly from myself and the sort of DSP team at Soraya in Cape Town, we're working very much in this space. And I think if you're able to attend the discussion group later on, I think you will certainly be bugged with many questions.
Sounds good. I'd be happy to.
Cool. Thank you very much indeed. Again, if anyone has any questions outside of this, either drop it in the Zoom chat or on Slack. Mike's fairly responsive on Slack, I'll have you know. So that's pretty cool. Thanks again, Mike.
You're very welcome.
And I guess on to the next one is Tyrone from Cape Town. He's going to be speaking about, well, I guess, how the CBF Correlator Beamformer team has gone with MeerKAT and moving forward into the next generation of work. Over to you, Tyrone.
Thanks, Amish. Can everyone see my screen? Okay. Good afternoon, good morning, and good evening to everyone, depending on where you are. Yeah, my presentation sort of serves two purposes, or at least that's my intention. The one is to sort of, as Amish mentioned, take you on the journey that we as the DSP team at Soraya sort of went on over the last year as we starting to design and develop our new correlator system, and also serves as a precursor for some of the talks that you'll hear throughout the rest of the conference to sort of just give more context. You'll see a lot of talks, particularly coming from Soraya and some of our other collaborators around GPU correlators. So this is just to sort of give some context into that. Okay, just a quick outline. I'm going to quickly introduce the MeerKAT extension project. It's the new sort of project that we at Soraya are undertaking. And then I'm going to talk about the next gen MeerKAT extension correlator beamformer and sort of just touch on why we need this, how can we achieve this, the architectural options that were considered, and then delve a bit into the high level design for the correlator and talk a little bit about the processing nodes. I should just, again, just preface that I'm going to gloss over a lot of things because there are talks that will cover all of this in a lot more detail. So I don't want to steal the thunder from my colleagues. All right, so what is the MeerKAT extension project? So I'm going to assume that a lot of people on the call are sort of familiar with the MeerKAT project. If not, feel free to bug me on the Slack channel and I'll tell you more about it. But basically MeerKAT extension is, as the name suggests, sort of an upgrade or extension to the existing MeerKAT radio telescope. It's a collaboration between South African Radio Astronomy Observatory, the Max Planck Society, as well as the National Institute for Astrophysics. So there's 3 partner countries that are involved. It's sort of a stepping stone toward SKA mid. The intention behind it is to advance the SKA mid construction schedule and to mitigate some of the risks associated with the dish structure as well as other integration between the other subsystems. It aims to sort of enhance the MeerKAT system's performance and science capability. The big change really is moving from 64 antennas that we currently have on MeerKAT to 84 antennas. And the additional 20 antennas that we're adding will be the 15-meter SKA mid compliant dishes. And so we'll have an array of 84 antennas that will sort of be heterogeneous with the existing MeerKAT dishes as well as the SKA mid dishes. And this heterogeneous array will provide a test bed for future SKA calibration and imaging pipelines, because ultimately the MeerKAT dishes will form part of the SKA mid array. In terms of baselines will be extended by up to 10 kilometers, which results in a maximum baseline of just under 18 kilometers. Where as far as possible, the aim is to reuse a lot of the existing MeerKAT infrastructure. Unfortunately, the correlator isn't really one of those places where it is possible, but we'll get into that. And one thing that is emphasized, throughout this project is that it has as little impact on the existing MeerKAT operations as possible. Okay, so this is sort of just a quick summary slide of the current MeerKAT, sort of digital back end where we have the dishes. They get into the incoming antenna data is digitized by the digitizer subsystem. There's a switch inside each of the pedestals, and that transports the digitized data to our Karoo array processing building, where we have the Correlator Beamformer that consists of the 40 gig Ethernet interconnect, as well as SWRDS, where we do our real-time digital signal processing before we send the correlated data onto the science processing subsystem where they perform imaging. So as I mentioned, for MeerKAT extension, we will require a new or upgraded correlated beamformer, and there's a couple of reasons for that. One is that our existing hardware, which mainly comprises of SWRDS and 40 gig Mellanox switches, is only really spec to run up until 2025. And we expect that the MeerKAT extension project will be required to run much longer. Support contracts have started ending or will all sort of run out again 2025. So there's a sort of a maintenance concern there. And sort of one of the biggest driving factors is that the current MeerKAT correlated beamformer doesn't support non-powers of 2 numbers of inputs or antenna. So 84 antennas will not be possible, and we don't have enough resources to build the next biggest subarray, which would be 128 in our case, to support that. We could possibly rework the existing FNX engines on SWRDS, but it will require significant rework, and also possibly next-gen SWRDS, as we sort of on the cusp of resource limitations on that platform. So sort of a high-level concept for MeerKAT plus then the correlator. We started out with the idea, and you'll see that the early parts of the back end are sort of relatively largely unchanged, where we'll still have the incoming digitized data. We'll then still have a multicasting core network switch, but this is where it gets, where sort of the new bits come into play, where instead of having these SWRDS, which are the FPGA-based processing nodes, we could have sort of CPU, GPU servers, or even ASICs. And this is sort of what we considered at the start of this project. And I'll sort of walk you briefly through how we came to the ultimate conclusion of what our architecture is. So initially, our idea sort of was to use off-the-shelf servers. There's been a lot of work that has gone into, or GPUs rather, have developed over the years to be more attractive compared to FPGAs for some processing applications. And then there was also the influx of FPGA accelerator cards like the Xilinx Alveos, sort of these FPGA daughter boards that you could slot into servers. So the idea was that we would populate off-the-shelf servers with these FPGA accelerator cards that came with 100 gig NICs built into them, and possibly DMA data from those accelerator cards into the GPU for further processing. So our initial intention was to use these FPGAs for the F engines, and then use the GPU accelerator cards as X engines. The FPGA accelerator that we considered was the Xilinx Alveo, and this was sort of towards the end of 2019, early 2020, where we started considering these cards, and in a few months, we sort of ruled them out as a alternative, or not an alternative, but an option at this stage at least. And there were a number of reasons that fed into that. One being that the tools, the Vitis tools, wasn't yet mature enough for what we needed it to do and accomplish. And the other reason was that DMA over PCIe wasn't actually possible on the class of GPUs that we were using. So we like to use the consumer-friendly or gamer GPUs that are much cheaper than the professional enterprise cards. And the vendors actually lock you out from using DMA on those cards. So that plan sort of came to an abrupt end. And when we sort of eliminated FPGAs from this architecture, we introduced 2 major challenges. One was the F engine to X engine funnel in problem, where we have multiple F engines sending data to the same X engine at the same time. Wasn't so much a problem with FPGAs because we could precisely control when data is transmitted, and ultimately result in no packet drops, but not so readily accomplishable with a server, a CPU and NIC. And then also GPU F engine implementation. Very little work has really been done in that area. So that was sort of a high risk design or development concern for us. So yeah, it's been a lot of R&D going over the last few months. And it was sort of just to address those 2 challenges concerning the F engine predominantly. As I mentioned, the one was the funnel in problem. And it turns out that through investigation and using sort of more recent versions of professional network interface cards, we found that if we synchronize servers using PTP well enough, then we could actually define windows of transmission for each server and basically get over the funnel in problem. So it turns out that if you have a fast enough CPU with enough RAM and NICs with the correct feature set, you can actually do this in software as long as your transmitting nodes are actually synchronized with PTP. So that was one sort of challenge that we had overcome, and we suspect that this will actually get easier as newer generations of NICs and switches become available. On the GPU F engine, and again, I'm not going to delve too deeply into this, a rough prototype was implemented by a colleague of ours at Sereo, Bruce Merry, and this sort of de-risked a lot of the design around the GPU F engine. We've got a PFB or polyphase filter bank, along with many tricks for achieving the kind of parallelism that we need. And then also all the processing like fine delays, transposing, interleaving the two polarizations, and 8-bit quantization. There were a number of components missing from the initial prototype, like DDC for narrowband modes, as well as the coarse delay right at the start of the chain. But as I mentioned, this is, and you'll see tomorrow, I think when Andrew gives his presentation, that this is quite a complex design and it will get its own presentation. So with those two challenges sort of addressed, we then decided on this as our unit of compute or processing node for the next gen correlator. And as you can see, it consists of 2 GPU accelerator cards, a 100 gig or 200 gig NICs, as well as a multi-core CPU and sufficient system RAM. This slide just looks at or introduces tensor cores, but I'm not going to really look much into that in the interest of time. John Romain has a presentation on that tomorrow as well. But basically, the X engine wasn't as much of a risk for us because of the existing X GPU library that's well known in the sort of radio astronomy instrumentation space. But John Romain has done a lot of great work on using the tensor cores available on NVIDIA's latest generation of GPUs. And yeah, the performance speaks for itself. Even when trying to process over 1,000 antennas worth of data, we still IO bound when using tensor cores as opposed to the X GPU implementation on the same GPU. So yeah, look forward to more on that tomorrow. And then, yeah, so after we sort of had these stages of R&D and mitigated some of the key challenges associated with building a new correlator design using these accelerator cards, we proposed sort of 2 architectural options. One was a pure GPU correlator with a new 100 gigabit Ethernet interconnect. And there we would use the GPUs for FX and B engines. And the other option was to sort of upgrade the existing MeerKAT correlator, where we basically use the existing SCARABs as F engines and then use GPUs for the X and B engine implementation. And that will all run on the existing 40 gig network. Ultimately, the new pure GPU correlator with a 100 gigabit Ethernet network was selected by Sereo as the way forward for the correlator. So yeah, so I see I've got sort of 2 minutes left. So very briefly, this is what our new or next gen correlator architecture actually is going to look like. We've got the incoming data from the antennas after being digitized, both polarizations. With our current data rates, a 100 gig NIC can ingest 2 antennas worth of data, and initial resource estimations with our F engine prototype shows that a single GPU can process up to 2 antennas worth of data for both polarizations. So it maps quite nicely to say that one GPU can process all the data coming in on a single 100 gig port. So yeah, so we pretty much each GPU can give us 2 engines worth of compute, if you will, and that's the same story for the X engine architecture on the other side. Yeah, I'm not going to really go too much into detail here, sort of just to pave the way for what's going to be coming. But this is the F engine pipeline that we have implemented and are busy implementing on the GPU. Same with the X and B engine pipeline. Again, we've predominantly move to using the tensor core implementation that John Romain has been investigating. This is a node to engine mapping. Not really much to say there. This sort of just shows how the data dates that I mentioned map to the on the ingest side, and how the data gets split to the 2 GPUs in our server. I think my time is up. Amish, you must just stop me.
I think so as well.
Yeah, I'm sort of just going to skip over then to the end, where it's really just a summary of what's happening. The slides that I haven't showed just sort of touch on the hardware. But yeah, so going forward, the new correlator that we're building will be entirely GPU based for now, at least. Soraya is still continuing with work on the Alveo. It's still a viable candidate. So we have a team working on that. There's going to be 100 gigabit Ethernet interconnect using the same closed network architecture that we currently use for MeerKAT. And some of the highlights are that we'll be able to support an arbitrary number of antennas. We'll have at least the same performance as we have with MeerKAT, with opportunity for improved performance as we move to floating point DSP, can have more bits of precision. And it's also sort of a more flexible architecture in that new modes can be implemented on the fly without long FPGA compile times. And it's more scalable and readily upgradable, and ultimately minimal impact to MeerKAT. So yeah, thanks for your time, and apologies if I've sort of rushed over everything. I sort of wanted to just touch on bits of everything so that there's some context to what you will hear through the course of the week. Thank you.
Cool, thank you, Tyrone. Yeah, like you said, myself, Andrew van der Beel, James Smith as well, and even John Romain, we're all sort of speaking about topics that Tyrone has mentioned. But there are questions in the chat, Tyrone. I would encourage people to copy them over to Slack, because easier to keep track of questions there. But if we could move swiftly along, Wesley New, also from Cape Town office at SWRDS. He's more in the electronics team, and in my experience with him, spent more time with the SCARAB development, but I think moving on to Alveo, as the title slide suggests. Wes?
The flipping mute button.
Good to go.
Great. Good afternoon, evening, morning, wherever you guys are in the world. Thank you for tuning in. Please, if you hear children in the background, excuse me. I'm sure you all have had that experience working from home. Interesting times these days. I have been asked also to include my colleague and manager's presentation in mine. Adam Isaacson is unfortunately ill and in ICU at the moment, so please spare a thought for him. So I have tried to make it flow through the presentation, and I will first be going through some material that I know he would want to have presented, and then move into a bit more of what we're doing with the Alveo. And if you do want to get involved, please contact me if you like what we're up to and have a use for the Alveo. Great, so just an overview. We're going to just look at wrapping up the scope. There's a few more features and things that have been developed over the last year. And then I'll just touch on the little bit of remaining work that we are doing. Just look at our move from SCARAB development to Alveos. I know Tyrone just said they're not keen to use Alveos in their GPU implementation of the correlator. They've decided to move away from it, but we are still using it as a risk mitigation factor, and I'll deal with a couple of those in the presentation. The MeerKAT extension requirements, I think Tyrone's covered those quite well, so I'll probably gloss over those. And then I'll just have a look at the Alveo and the Vitis tool flow. It's a bit of a different mindset and design methodology to the previous Vitis design flow, as well as the Casper Simulink MATLAB flow that we use. So we'll just touch on that. And then I'll just give you a bit of an overview of our proposed F engine on an Alveo, as well as how that would fit into some of the architectures that Tyrone was just showing us earlier. So in terms of wrapping up the SCARAB, we feel the SCARAB is in a really good place at the moment. There's been a lot of effort put into completing it and really maturing the support for it in the tool flow. Things that are noteworthy, we've had all 40 gig cores can be utilized now independently, as well as the 1 gig interface. So if you put the 1 gig interface, or if you put down a 40 gig interface, you don't have any 1 gig interface hanging around underneath you. So that frees up some resources for your DSP and other things. Parallax has also added support for a second ADC that is supported on the SWRDS. It's a 14-bit ADC. It runs at 3 gigasamples per second. If you want more information on that, I know the INAF guys are using it and have tested, I think, their first batch of SWRDS delivered with the ADCs. We also support multiple ADCs, and Parallax has done some good work with the synchronization between ADCs on different boards as well as on the same board. If you are interested in that work, contact me. I can put you in touch with Parallax or anyone else who's working on it. There has been a lot of cleaning up of timing parameters and constraints, just tying up all the loose ends and critical warnings that we were getting, as well as p-blocking and constraining particular aspects of designs. Then a lot of work has also gone into the documentation, the tutorials. Matthews has particularly done a lot of work on the spectrometer tutorial, and I'll show you that just now. So we are quite happy with where the SWRDS is. It's well supported, and we feel that we are happy to support people using it, and we'll have minimal comebacks. So if you're interested, there are 5 tutorials. Matthews is busy working on a wideband spectrometer for the new ADC, which should be up shortly. So as Ty was speaking about earlier, MeerKAT extension being built with GPU, F engines, and X engines. There are some risks associated with it, and I think Ty had the time to go into the details there. But particularly with regards to the power usage, we are constrained for power in our career array processor building. We are out in the middle of nowhere, and we are quite restricted there. So that is one of the things that has been identified as a risk, and the reason that we are looking at Alveos as a possible replacement if those GPUs aren't able to solve or work for us there. The other thing Ty mentioned is that an Alveo on a F engine on a GPU is relatively new territory, and there are proof of concepts that the guys have done that are looking good. But again, another risk mitigation is the Alveos. So our electronics group is working on an Alveo solution, and we were looking at kind of incorporating it into the Casper environment, and we'll touch on that now. So there's just a picture of the U280. I think Tyrone had one of those as well. That it actually takes up 2 slots. It's just physically large with all the cooling on board. More people are tending towards the Alveo U50 these days because it's more compact, although it is has about half the resources in terms of LUTs and DSP slices, etc. There's a bit of the Xilinx product table of the Alveos. There are a few more now, but we are currently developing on the U280 and the U50. There you can see about half the resources. But also the key thing is about half the power. So look, generally you don't fill these things to 100% capacity. So yeah, if you can get away with a smaller card, you generally will be better off. Excuse me. So we decided to go with particularly off-the-shelf cards because we've had a history in Soraya of developing our own hardware. And just looking at the next generation of FPGAs, the ultra scales, they're quite expensive. This pricing is probably a little bit old now, probably a year or so old, but with these Alveo cards and a lot of the off-the-shelf boards, you can pick them up for a fraction of the cost of buying the FPGA. So we kind of have started looking quite a lot into the off-the-shelf boards, and the Alveo stood out as one that could work quite nicely. The PCIe is also quite an attractive feature for us, particularly because we can integrate them into a server and quite easily develop hybrid systems with our GPUs, rather than the SWRDS, which are more standalone. So there are quite a few COTS boards out there, and Mitch has already spoken about one or two of the RFSoCs. I'm not going to go into the details here. for time. But there's a number of them, and a few of them actually have support for Casper, as Mitch has done a lot of work on that, and others. And another, I guess, prime example is a RepTire, technically off the shelf. If anybody is interested in getting into the Casper kind of tool flow, get yourself a RepTire and you can use all the yellow blocks in the MATLAB Simulink design flow for that. And there's some great tutorials online. So we initially started off with the Alveo boards, and we wanted to develop them in the kind of traditional FPGA mentality and methodology. And we started developing them with Vivado and writing HDL as a lot of our team members were comfortable with. And we managed to brick 3 of our Alveos. And this was actually just using example designs from Xilinx. Unfortunately, we weren't able to recover them at our labs or at our offices. We had to ship them back to Xilinx. They have subsequently apologized and even sent us an extra Alveo card. But just that kind of experience really put us off developing for these cards with Vivado. So it's forced us into looking at Vitis and just reassessing the way that we design and develop. Vitis is quite a different mindset. Let me just jump down a couple of slides. So the idea with Vitis is you kind of write your application in HLS or almost a high level language, and you kind of set aside different aspects of your algorithm to run on different platforms. So part of it will kind of run through the Vivado tools, the general synthesis and place and route and all that, and run as a shell on your PCIe card. Your application code then that will run on your CPU gets synthesized through your normal GCC or G++ compiler, and that runs on your host, and they interact through the Xilinx runtime library. So it's not your standard RTL mentality of design, but it's quite a different way of thinking about it. And so it's taken us a bit of time to get our heads around it and into it, and we've done a couple of courses, and it's been pretty good. But we kind of have been looking at this saying, how can we integrate this into the Casper tool flow? So let's just jump up a bit here. So we really want to keep this development as part of the Casper collaboration and be able to share the work we do. But we just feel like this design methodology with Vitis is not as compatible with a MATLAB Simulink graphical interface as it was with the previous way of developing. So we're looking at going with kind of a raw Vitis development flow, but the idea being that we create DSP libraries. So I'm just kind of getting ahead of my slides, but the idea is that we want to keep giving back to the collaboration, and we want to be able to share what we've done. So the libraries that we will be creating will either be pulling from the green blocks, the existing Casper green blocks, and using those as HDL and generating kernels that will be that can run on the Alveos, or generating new HLS blocks that are parameterized and configurable that we can in turn share back into a library that the rest of the collaboration can use. So just to get back, Amish, how much time do I have there?
You got 3 minutes to go.
Okay, cool. 2 more slides, cool. Okay, so just to give you an idea of how the Alveos can fit into a hybrid architecture, Tyrone spoke about having their GPUs and Ethernet interfaces in their host machines. We can very easily slot the Alveos into the PCIe slots. They have 100 gig Ethernet ports in them. Most of them have dual, so 2 100 gig Ethernet ports. And we can also send data over PCIe between the GPUs and the Alveos on the same host machine. And this is quite a scalable solution. You can have as many host machines as you want, as long as your switching architecture, your network architecture supports it. And you can put as many Alveos as you can fit in, and GPUs and Ethernet interfaces into your servers you can fit there. The D engines, obviously, you sticking to the Casper interconnect methodology of 100 gig or gigabit Ethernet switches. It's just let the commercial guys do that for us, and we don't have to worry about our interconnects. So drilling down into the Alveos, just last slide quickly. Here's our proposed kind of F engine architecture. There's your software running on the host machine. You do your control over long gig Ethernet. We're planning to use CAT-CP to speak to a TCP raw server kind of server that will be integrated with host code. We're still kind of thinking and designing that one, figuring out how that will look. That'll speak through the Xilinx runtime library over the PCIe to do control of your processing pipeline as controller, as well as control and configuration of your Ethernet core. And then the idea is to have AXI streaming interfaces between all of your different processing blocks. And what we're looking at doing as well is standardizing these to AXI streaming. In the current Casper toolflow, we don't actually have that standardized, and every block has its own interface. So you've always got to do a bit of tweaking when you're connecting up different green blocks. But the idea would be to try and standardize this. And I think this is also a good idea. You could do it in the actual Casper toolflow with those green blocks and maybe update them. But yeah, the idea is, and then you can stream it out over the PCIe as well to GPUs or whatever else is in that box, or you can stream it back out over Ethernet to another server. Yeah, thank you. That felt very rushed, but that's it. Any questions?
Cool, thank you, Wes. No, I mean, I think you got through the gist of it. I see there's a question in the chat from, God, I scrolled past it now, sorry. Yael, if I've pronounced that correctly, can Vitus be used with system generator? I can't remember off the top of my head.
Funny enough, Adam sent me a link to something like this a week or so back. I haven't actually had a chance to go through it, but there is some way that they can integrate it. I can send you the link if you would like. I see there's another question there, an Alveo like RFSoC board. Mitch is probably better positioned to answer this question. I'm sure there are RFSoCs with PCIe interfaces on them, if I'm not mistaken.
Oh, yeah, that's a good point. But yeah, if you could drop that sort of Vitus with sysgen in the Slack, the workshop Slack channel, that would be great.
Great.
But
thanks,
cool,
guys.
Again, yeah, thank you, Wes. Anyone else has any question for Wes?
I just want to take this opportunity to punt. We are going to have the hardware discussion afterwards. If anyone is developing new hardware and kind of wants to chat about what they want and their specifications and requirements or ideas, popping along to that. I think we're having it after the session. So yeah, please bring your ideas and stuff to that discussion. Thanks.
Definitely. Thank you very much. I was going to do the same as well, because that's something I'm keen on attending. I think from there, some of you might have noticed when you registered, if you chose the option to present, you also given an option to present a shorter talk or a sparklet presentation, which we aim to replace the usual poster session. So we've got, I think, 3 submitted, pre-recorded poster-esque presentations so far. One from Homan Jiang, who most of you might know quite well, does some very cool work with ADCs. From Kirsten from JPL, she works quite closely with Melissa, if I remember correctly. But yeah, whoever's sharing at the moment, Melissa, I think that's you. Yeah, please do go for it.
Wesley, need to stop sharing first.
That's not me, Dan. I think I have stopped. Yeah, I've stopped sharing.
Yeah.
Okay, you ready? Are you guys ready?
Yeah. Mhm.
Per second AD. HIA Taipei, Taiwan. I'm going to show you the 16 gigasample per second spectrometer based on the Casper technology in 2 minutes. When use the VCU11 as the platform, and the spectrometer is 2K channel, 8 GHz bandwidth. We have developed the 16 gigasample per second ADC FMC interface board. And we are using the Casper Jasper library totally with 64 output and input. The time domain and frequency domain data has been tested, and the data is look good. The yellow bar for the ADC is ready, and we are using the 1 GHz length developed by Jack. And this is a 16 gigasample per second ADC. We are using the Lentex 7123 4-bit, and the E-node is from 2.5 to 3.7 bits. We have published a paper. The link is here. If you're interested, you can take a look at this. This is a photo of the spectrometer, VCU11A and 16 G ADC. This Casper Jasper model file, 16 giga ADC with 64 parallel output and the Polyphase filter bank and the WebT, then take a power, then accumulation. This tester setup, noise source, tunable attenuator, tunable notch filter, then the VCU11A platform and the 16 G ADC, and 1 G Ethernet for communication with the computer. This spectrum captured by the spectrum analyzer for the comparison purpose. The 3 spectrum was captured by the Vivado iOS software for the comparison purpose. The 3 spectrum was captured by the Casper model, and compared with the previous 2 slides, they are pretty consistent. Coupled with a call for help in the Casper developer group, and later on I examined the 16 gig ADC yellow bar, and I find a bug in the yellow bar. So the bug is in the ADC yellow bar, not in the Casper FFT bar.
Melissa, we lost the audio, or maybe that's the end of the talk.
Yeah, I was just going to ask the same thing. Do you want to maybe skip to the next one? We can come back to this.
Looks like there was one more slide, but I think that's okay.
Okay. So we'll go to the next one.
radio astronomy spectrometer deployed
NASA's Canberra Deep Space Communications Complex. A high-resolution spectrometer was installed and commissioned at NASA's Canberra Deep Space Communications Complex, or CDSCC, in November 2019 to enable spectroscopic capabilities. The spectrometer is comprised of 4 Casper Roach 2 boards that process a total bandwidth of 16 GHz. The spectrometer samples and processes data from CDSCC's 70-meter antenna and K-band front end, covering frequencies of 17 to 27 GHz. The system has 2 different firmware modes, a 65K point FFT that provides 32,768 spectral channels, and a 16K point Polyphase filter bank that provides 8,192 spectral channels. The firmware utilizes the tool flow. Software modules were developed to control the spectrometer observations and to enable its operation within the Deep Space Network's infrastructure. The spectrometer is autonomously controlled through a configuration file, which includes information such as observation schedule and firmware mode selection. The output is recorded as binary data, which is then converted to single-dish FITS format and GILDAS class files for storage and processing. The left image shows the on-the-fly mapping of Carina Nebula. The image shows 1 to 3 GHz radio continuum emission in the color scale, and our current radio recombination line map is shown in contours. The image reveals the kinematics of ionized gas in Carina Nebula. This is a work in progress, and we want to cover the whole region and combine with ionized nitrogen data taken from Astros NASA balloon project. Thank you.
Awesome. Melissa, do we have one more submitted Sparkler presentation?
Yes, that's right.
Hello, I will be talking about filter bank as an MP4. MP4 is just a placeholder for all the video encoding standards, and those were actually developed to have to manage and store large video files on less and less spaces. So one straightaway benefit we see is that we end up saving a lot of space when we store a filter bank as an MP4 file. And the second thing is that of streaming. Imagine if you have two geographically separated radio telescopes, and if you can possibly do filter banking at both the telescopes, you can send those filter banks as an MP4 stream to a central location to do processing or searching, so FRB searching or pulsar folding and such things like that. And the bandwidth requirement for that operation would be much less than sending actual filter banks. So how would you go about it? We actually interpret every we take a 2-dimensional array out of a filter bank, say of n channels and n SAMs, which is the number of channels and the number of samples. And then we interpret that as a Y channel of a YUV frame. And we set U and V's to be 0, so there's no color information. And then we send that through a encoding pipeline so that we get our MP4 file out of it. And if we do all of that, we end up getting something like this. And this, the x-axis is the time and the y-axis is the frequency. And if you are smart, if you're fast enough, you can actually see the broadband and narrowband RFI. And if I play it at 0.25 speed, we can actually see the RFIs that come. And in this, I've used the H.264 standard and using FFmpeg. So if we talk about the compression ratio, we get a minimum compression ratio of 0.25. And we also get a near constant mean squared error. The way I compute the MSE is essentially take the original frame and then pass it through the pipeline to convert it to MP4 and then convert it back again into filter bank, and then do a MSE between those two frames. And that is near constant for each backend, which implies that there is a scaling bias involved for each backend that the current pipeline doesn't take into account. And lastly, when I send just pure Gaussian noise with the 512 number of channels, we still end up getting the same compression ratios, which implies that this is non-entropy coding, and we have sort of compressed the Gaussian, which is not compressible, the Gaussian noise. The future outlook of this is that before we proceed any further, we have to understand the effect on searching and calibration, because if they end up messing with that, then all of this is a no-go. We have to try out different codecs and standards and see which one works the best and which one is more suited for this operation, and just so that we have better idea. And then we can also end up compressing voltages if we encode the phase and as a colored component of it. Ideally, when you're doing a Stokes I or magnitude filter banking, you're just taking the magnitude of it. But if you also store the phase as a color, then you can end up compressing voltages. But there are I4C2 limitations which are kind of hard to go about. One of them is the 8-bit limitation, where every sample should only be of 8 bits. And this is mainly because of all the codecs kind of assume that you are dealing with 8-bit per sample. And the second limitation is out of Stokes I, because there are 4 Stokes in any color model has only 3 components, so you can't really put 4 into 3. So that's about it, and hoping.
All right. Awesome. Yeah, I think, well, certainly Kristen is around to take any questions on Slack. Homan, unfortunately, is quite far east, so he's probably asleep now. And the last presenter, I couldn't find you on the participants list, but please do drop any questions on the Slack channel. I think we'll break for 15 minutes now, and after the break, Patrick Lysaght from Xilinx will be giving us a talk. But thanks again to all the speakers from this session. That was very cool. Until then.
All right, now let's welcome Patrick Lysaght from Xilinx, who has given talks at many Casper conferences, and we're honored to have him in our first virtual workshop as well. Thank you, Patrick. Take it away.
Thank you, Catherine. Can you hear me? I'm coming through.
Yes.
Yeah.
Loud and clear.
Great, thank you, and thank you to Catherine and Dan for the invitation. It's a pleasure to be back, albeit virtually. I think the last time I was at was in Boston and Harvard, and I remember the nice walks along the seafront on the way there. I missed that, but let's get started in the interest of time. Let me just get my screen going here. Screen. Okay, so let me go into presenter mode and arrange the screens. Okay, hopefully you can all see that.
Indeed.
Okay, great, thank you. So I'm going to talk about accelerating the design of state-of-the-art instrumentation, and you know, we're lucky enough to have worked with the Casper folks and the radio astronomers for long enough to recognize that you do some really cool instruments, and that the kind of engineering you do make us envious of your abilities. And we have Jenny, Jenny Pearl-Smith, who was talking earlier this morning with us at the moment, and you know, we look at her work and seek inspiration from it. So the two technologies I think that might be of interest to this community. The first is a recently announced new set of products from Xilinx called the Kriya system and modules. And I'll go over what that means and the first member of that family, which is the Vision AI starter kit. And that is the KV260, and the K26 is the sound that's associated with that starter kit. And then talk a little bit about the development flows there, because I think some of what's being said is relevant to the direction that Casper is interested in particularly the hierarchy of skills that you might find in the development team, and the assumption, you know, you can't make the assumption that everybody has deep Vivado and hardware design skills. So how people are evolving to accommodate that. And then I'll switch to talk about the RFSoC 2x2 project. This is a new open source project that tries to make the Zinc UltraScale RFSoC capabilities more easily available to a broader academic community. And as part of that, we've got a software component to the project as well, which we call RFSoC PYNQ. And there we've been working with some developments in data analysis and bringing those back into the instrument side of the house. And effectively, we think we found a way to practically speed up the creation of new instruments. I wanted to share what we're doing there and show it to you, and some ideas and suggestions we have for how that could be useful. And then finally, we'd look at some next steps. So the Kriya module then, this is very new, launched in the last month or so. And in essence, it complements the Xilinx portfolio. We've had obviously devices for a long time. We started producing boards 2 years ago, and I think I spoke a little bit about the Alveo series 2 years ago. And what's different, say, between the Alveo board here in the center, the accelerator card, and a regular development board is that a regular development board is really intended to help somebody get to use the chip in another application. So ultimately, you are going to do a chip down design, whereas in the case of the accelerator card, that is the product, that is the end thing. So a development board isn't supported, for example, for 10 years, or isn't, you know, certified to work in a range of environments. And so the new member of the family then are the system on modules. And the first of these is the Kriya KV260, as we mentioned. And again, these are deployable entities that are production ready. So this is the KV260 starter kit that you're seeing here, what you would typically develop on. It has a big heat sink on, the big red thing with the fan, and well, maybe a big fan, because in fact the heat sink might be underneath. And then the SOM itself, which you can see with the 4 holes, corresponds to what you're seeing on the right here. And the idea is that you would start by developing your design on the AI starter kit, and then once the design has reached a point where you're confident with it, you could deploy it using the K26. And this has obviously tremendous benefits. The key one is that instead of doing a chip down design, you're now doing a module based design. And of course, you have less work to do. You can get there faster, and you can focus on your value add. And things like, for example, power supply design, which are non-trivial for advanced devices like zinc ultrascale, clocking, etc., DDR interfaces that take quite some time, and we all know about this. We're currently doing some of this ourselves. Are taken out of the loop, and then you get a production qualified part with long lifetime and ruggedized, which we'll see a little bit more of shortly. So the benefits of the SOM, I think, are significant as the complexity of the design increases, and the skill set to pull these off is a little bit less available, and the value add is actually somewhere else. The value add isn't in the PCB design. So typically we're seeing a broader market. When it was chip down design, it was FPGA designers. When we're talking about things like the Kriya, it could be somebody wanting at the edge to accelerate a neural network application. So there are a lot of edge scenarios where GPUs and PCs just don't cut it, typically because of performance, power, and latency requirements. And these kinds of SOM solutions are focused on those kinds of applications. Now, the one that you're seeing here is an AI vision kit, but this is the first in a proposed family of Kriya SOM modules. And so we see the software developer being able to get up and running more quickly. We want to minimize, if possible, what is required of the software developer. And for the hardware developer, he's got a much simplified task. And effectively, you save his resources for the other parts of the system, like the carrier card that this SOM would typically interface with. So the intention, obviously, is that the development carrier card isn't the carrier card that would be deployed. So this is what comes out of the kit, the starter kit. It's another view of what we saw a moment ago. You see a carrier card, a development carrier card, with a version of the SOM here. You can see that the big red fan is removed, as is the heat spreader. And this is designed really just for development, this environment. Actually, even the SOM in this case is a slightly defeatured SOM. It's not the production SOM. And the whole idea of this is that it's tailored to the end application space that you're trying to explore with this application. So in this particular one, as we said, this is about vision. This carrier card is highly optimized for camera inputs, etc. And it would be different if you were targeting a different application. So a lot of emphasis has gone into delivering something which is usable by the application or domain expert, so that out of the box it would be possible for them with this particular deployment to actually be running software and applications within the first hour. And this is something that we will spend more time on going forward at Xilinx, but I'll also mention more of in the slides that we have here this morning. So we see a hierarchy here. Excuse me. It is possible to approach this board at the most abstract level, right down to the lowest hardware level. You can customize different aspects of it. You can change the hardware design if you want. But the intention is, where possible, to support people who don't have to change the hardware, to allow AI developers to use this, for example, as is. They might load new AI models, for example. There's a DPU in there, a deep processing unit, a soft IP block from Xilinx that accelerates neural network applications. You can specify the designs for that in PyTorch and TensorFlow, and you can live at that level of abstraction. But if you need to, and if you want to, it's possible to go further and customize the software, and indeed customize the hardware that's in the device as well. So I guess success at some level would be delivering as much of the top level experience as possible, and minimizing the amount of bottom level experience that you have to do. This is part of a bigger campaign, if you will, to actually try to come up with applications that are provided both by Xilinx and third parties. to give those third parties a target that is a stable target with longevity and attractive pricing, so that they can bring their expertise deployed on the platform and then make it available to third parties. And these are some of the applications in scope as we stand. Now, there is a caveat here. If you look at the small bullet that says 2, it says application coming soon. And that applies to several of these that you see here. So the intention is that these will be available shortly from Xilinx. The first 3 are available now, and then also from our third parties. So the intention here is to try and create a reference platform that other people can use and exploit. And in some ways, this is a parallel to what Casper has done. You know, many years ago, Dan and the team observed that it would make sense to have some generic platforms that could carry the workload for a variety of experiments, and then to invest in the software infrastructure, you know, your famous yellow blocks in your flow that could be reused and reused across the projects. So in some cases, this is very familiar to the Casper community. The good news around this is that the kit itself is $199, which is very competitive. There's an MPSoC device under here, which I'll mention in just a moment or two. And the SOMs are offered in 2 production grade categories, a C grade and an I grade. And the C grade is the one that goes from 0 to 85 degrees. That's the commercial environment with a 2-year warranty, whereas the I grade is -40 to +100 degrees. So that's quite a rugged spec. And you see here the aluminum heat spreader that's been placed on top of the SOM image that you saw earlier. So this is what gets deployed. This is, and the intention of the development platform is not to deploy this. This is not supported with these kinds of specs. In fact, this is just supported for room temperature development. And this Creo-SOM is slightly more featured than the one on here as well. So we'll see a little bit more of that going forward. So very attractive for the capabilities of these platforms. In terms of the carrier card, which was just for a moment to emphasize that this is the carrier card here on which the SOM is located. So we're now talking about the carrier card. The carrier card has the SOM. This is the inner bonding blocks. See that the SOM has DDR4 built onto it. It's got some 240 pin. These are Samtec 4x60 pin connectors. In fact, the fully featured one has 2, but the one on the carrier card has 1. And then it has a range of standard interfaces like Ethernet and USB, DisplayPort and HDMI, some camera interfaces, some other familiar things like PMODs and power and DC jacks, etc. And the idea is that this particular card is exposing, if you will, the SOM as a platform for AI vision applications at the edge. Other carrier cards would expose SOMs for other domains. So this is the thinking behind the carrier card approach. So the specifications then for the SOM itself, it is a Zinc UltraScale MPSoC device. One point to note here, and I want to be clear about this is a custom-built Zinc UltraScale MPSoC that runs optimally and exclusively on this K26 SOM. So you will find it in you will find support for this board in Vivado, but it's not a standard part on here. But it's got all the features you're familiar with from the MPSoC, the quad-core 64-bit A53s, the dual R5 real-time processors, the GPU, which is the ARM Mali, tons of system logic, the deep learning unit, the DPU, which I mentioned earlier, which is optimized for this particular AI application. That's a soft core. There's a video codec in this particular device as well. It does H.264 and on-chip memory and some various other features. And then there's a range of interfaces, which, as I emphasized earlier, in this case are AI vision centric. But you can see there's, for example, 40 gig offload capability here via 4 lanes. So it's quite some significant interfaces. The first ones are camera interfaces and a range of others down here. So that's the K26. If you're unfamiliar with the Zinc UltraScale, I think most of this community has exposure to it one way or another. But quick recap, these are the A53s, the R5s, so application processors and real-time processors, the Mali graphics, some platform config and security stuff, memory subsystem interfaces and system functions. So a whole pile of SPI, CAN, etc. And then you have the programmable logic. And in this case, it's a combination of things like the MIPI sensor fusion, the deep processing unit, and the hard-coded video block, which is actually in the fabric. So that's what's underneath the K26. And then in terms of ruggedization and how this is being delivered, this is really quite commercial, if you will, in the sense that this is ready for deployment, depending on whether you need a C grade or I grade, and it will be certified in numerous countries. This is ongoing availability, ongoing planning, and you can see here that the warranties and the operating lives are quite significant. So availability for 10 years, etc. Warranty for 2 years on this one, 3 years on this one. These are very competitive and very significant relative to, say, a normal development platform. And of course, the connector technology and everything else is chosen to support these rugged specifications, or specifications for ruggedness. There's a ton of material. All you really have to do is Google Xilinx Kriya, but here's a reference here for the Kriya. Xilinx has invested a lot in trying to make this a really usable platform immediately. There's a ton of support material there, the initial designs that work out of the box. There's a wiki, there's a lot of training material. And this ecosystem is something, as you can see, when we committed to it, we've already committed to a 10-year life on this. So we're completely vested in this approach. We think it's the right thing to do right now. And I think for certain applications in Casper, this could be an interesting option. I think that in the past, for example, you've had compute modules that you had as daughter cards on board. So you've already had, to some extent, the SOM concept. And you can see that this echoes elements of what was previously done. And I borrowed this from one of the pages that I referenced a moment ago, or referred to a moment ago. The vision SOM isn't the only SOM that's anticipated. So here's one, for example, that's a custom optimized one with a view to electronic drives and other things. And then there are other ones that are anticipated for other applications like highest compute SOM. So this is meant to be a generic model. The KV260 is the first family member, but it's not intended to be the end of the game. So at that, I'll pivot. I'll go from the Kriya SOMs to the Zinc UltraScale. And again, I know that you are pretty familiar with this now. There are several talks, I think, this morning and throughout the week on the Zinc UltraScale RFSoC. And of course, the key thing here is the integration of these data converters, these RF direct sampling data converters that are in gigasamples per second into the same silicon as the fabric and the processing system. That's the key value add here, the integration. And one of the things we've wanted to do for a while is take this technology and make it more accessible in academia. I think currently the entry-level board is a ZCU111 and it's approximately $9,000. We've now launched the Zinc RFSoC 2x2. This is a board with 2 ADCs exposed and 2 DACs exposed at the periphery of the board. And we're selling that to bona fide academics at $18.99. So that's a very considerable reduction in price. We're also shipping it with the PYNQ infrastructure, the RFSoC PYNQ framework. And I'll explain that a little bit more in the coming slides and some of the benefits of that. And the idea there is to try and make this as accessible as possible to the scientists who want to use its capabilities, try to avoid having to do too many low-level things. And this whole project is open source, so we have a ton of tutorial materials. We want to make our design examples executable so that you can actually reproduce them, modify them if you want to, and there are several very compelling design examples. And all of this is currently available at rfsoc-pynq.io. So very briefly, the board is a relatively small board, 5.5 inches by 6 inches. Its main components are the 2 ADC and 2 DAC channels, some external clocking, and we've tried to keep this as compatible as possible with the ZCU111. So these are similar to the ZCU111 designs. 4 gig of PL and PS DRAM, and then of course the many power supplies that you have, all of which are instrumented, well, 12 of which are instrumented. They're actually more than, I think, 24 individual power supplies of different types on the board. The 12 main supplies are instrumented and can be monitored, and then this indicates the status of all the power supplies. There's a little CCG connector on here, which is kind of a poor man's FMC, intermediate really between PMODs and FMC, and then the usual Ethernet, DisplayPort, etc., and these other interfaces that you're familiar with. So the project website will tell you more about the board. It will also show you how to get started. Again, we have the objective of getting people up and running really quickly. And all of this material is open source, reproducible, and available to anybody. And we draw particular attention to our Hello World example, which is a pretty cool spectrum analyzer, a 4 gig spectrum analyzer, 2-channel. And we also have things like frequency planners that we've ported from Excel into Jupyter notebooks. And then you see some comms example. But we think the spectrum analyzer is a particularly good example because it addresses both the communications community and the instrumentation community. So we think it's a good Hello World example here. Talking about the software for a moment, I think most people by now are familiar with Jupyter, Jupyter Notebooks and Jupyter Lab. And essentially, this is the software that has taken the data analysis world by storm. And traditionally, it's run on a server or run on a desktop. What we've done essentially is said, this is a really cool framework. The kinds of things these people are doing, we want to do, but we want to do them in an embedded context with RFSoC. So what would it take to get this kind of environment running on an RFSoC? And that's essentially what RFSoC PYNQ does. So we port all of this so it runs natively on the ARM A53s here. And our goal really is to increase productivity by improving ease of use and ease of reuse. We want to take things that people are already familiar with, that are already successful for them, and reuse them in a different environment so that they can leverage their other knowledge. And I guess we should shout out that Jupyter and Jupyter Notebooks and Jupyter Lab, of course, were developed by physicists. So that in itself tells us something. And that I'm reminded by Jenny that physicists generate more big data than anybody else in the community with the SKA and various other things like CERN, and that you're going to need to do more of this now that the theory of matter is under doubt again. And key to this and the approach is interactive data analysis. Interactive because you're not entirely sure what the outcome is because you're trying to explore the data. Visualization is key because in many cases, being able to see things is a great way to analyze the data. And then it's all deployed using web standards. And this gives you openness and the very latest interactivity. And so we've taken this technology and ported it onto the ARM A53. So this is a standard kind of high-level architectural diagram of what goes on inside Jupyter. And then we connect to that over a browser connection. And this gives us access to the RFSoC. Now, what we've then done is we've made the interfaces to the RFSoC as Pythonic as possible. And Pythonic in this instance means that what I would expect to be able to do in Python on the software side, I would hope to be able to do in Python on the hardware side. I'd like to interact with the hardware. I'd like to query the hardware. I'd like to install things. So I'd like to do pip install Spectrum Analyzer, and lo and behold, a Spectrum Analyzer would appear on my RFSoC board. I'd like to be able to look at a dictionary and see what IP is in my design. I'd like to be able to query an entry in the dictionary and be able to see what the memory mapping of my IP would be. So we take this concept of being Pythonic because it essentially is a way of expressing the real value that Python brings and has been proven over time. And it's essentially this introspection. Python allows introspection and dynamic language benefits. And we want this for hardware. And that's what PYNQ does. So in addition to porting the Jupyter framework, we then integrate the underlying platform into the software environment as optimally as possible. And I think you've heard from a number of talks, and maybe we'll hear some other talks, that this is of value in the development of these platforms. So this then is our Hello World example. And you can see here we've got widgets which are controlling a tone generator, which you can see here in the output, and we're using standard tools, etc., to do this. And this is kind of a standard notebook, except now it's running coupled up to hardware on an RFSoC. So in effect, what's happening is the IPython widgets, which are specified in Python but generate JavaScript entities that run in the browser, are now linked not just to the state of the Python, but also to the state of the underlying hardware. So we can adjust the tone generation of the RFSoC directly from the web page, and we can track what's going on as well. There are times when thank you. There are times when the spectrum analyzer in the notebook is good, but you'd actually like to see a dashboard. It's possible to generate one of these with a single command. The result is something like this. You actually get your instrument front panel built for you with a single command. So this is exactly the same infrastructure that we're talking about here, transformed via the Voila command, which is a dashboard generator, into a working dashboard. And I'll try to finish very quickly with this example from our friends at the University of Strathclyde and just show you what this looks like. And hopefully I'll be good on time. Now, why doesn't this want to start? Here we go. Can I get a play option on this? Okay, so this, I was going to show you a short video, but I'm struggling to get it to go, and I seem to have lost my mouse. Okay, my mouse is back. Maybe because I'm on pointer. Hang on a second. Highlighter pen. Okay, so I'm out of there. Okay, let me try it this way. I'll go to present again. Are you still seeing my screen? Is that still displaying?
Yes.
Okay, great. So let me hit here.
So Patrick, there's no audio coming across.
Okay, I'm sorry. Let me go. So what you're seeing here is, correct. What you're seeing here is, let me go down again. The notebook that's associated with the spectrum analyzer. And this is a standard notebook. We can operate it either in loopback or with an external antenna. In this case, we're going to use the antenna in the design. And what we're going to do is from this notebook, we're actually going to generate the dashboard for this spectrum analyzer design. And we're going to do it automatically using the Voila software. Catherine, this is about a minute and a half, so I won't be too late. So here are the instructions on how to do this built into the notebook. There's a single command that you copy and run in your terminal. And we'll see that in just a moment. So we copy that. And basically, it will take all the active code cells in the notebook and execute them for you. So here's what happens. We grab this command. We then open a terminal window. Paste the command in there. And this kicks off the Voila server process, which is actually transforming your notebook into a dashboard. The dashboard will be served on a different port. So we can now go to that port address, which is 8866 in this case. And the processing is now generating for us a dashboard from the notebook. And it's actually opening the notebook, executing the cells, generating the HTML, putting in the code that will communicate between the back end and the front end. and finally connecting that all the way back to PYNQ and whatever overlay, in this case, the spectrum analyzer. And the key here is that the IPython widgets are tying the front end to the back end, as we saw a little bit earlier. And this is the result. And you see we have a fully interactive instrument front panel. And we think this is a new watermark, if you like, or watershed in rapid instrument creation. So fully working instrument front panel available to you from the, and I had some other demos, but I'll jump through them. Take my word that you can do this with a lot of different instruments and dashboards. It's really cool. And basically what you're doing is you're taking the best visualization technology from the data analytics community and effectively benefiting from that in your instrument design. So next steps, if you would like to know more, there's a ton of good stuff up on the website. For those of you who have already invested in ZCU 111 boards and feel left out, please don't. These designs work on the ZCU 111 as well. So you can download and install PYNQ and the designs and operate them there. And what we think we have here, and what we hope we have for the Casper community, is through Kia, some opportunities perhaps to be able to use SOMs to offlay some of the development costs of boards and focus on your key value add through RFSoC PYNQ to be actually able to generate and prototype new instruments more quickly. So for example, when I talk to Jenny about the spectrometer, we don't just talk about the GUI front panel, we talk about the calibration, we talk about the self-test of the design. These are important capabilities as well. And to be able to automatically generate dashboards for those we think would be very helpful. So with that, I'll conclude almost on time, I think, Catherine. So.
Thank you. That was a fantastic talk. And next we have a hardware discussion that Wesley New is going to lead. If you have a number of questions in the chat, and unfortunately there isn't time now to do a live Q&A, but if you would answer these on the Slack, it would be really great to continue the conversation that way.
I'll do that, Catherine.
Wesley, are you here?
Hey, Catherine, I am.
Hi.
Catherine, are we going to do it in this session, in this Zoom?
Yes, we're going to use the same Zoom, and this will be a focused hardware talk that anyone who wishes to stay on the Zoom for is welcome to join. But we'll just keep this Zoom room open, aiming for about an hour, but the Zoom will stay open if it needs to go longer.
Okay, great. Yeah, I think it's going to be quite a big discussion if all 81 of us hang around. So pretty much, guys, what I'd like to do at first is to start off with just getting some input from people who are interested in this discussion as to what you would like to discuss and what you'd like to bring to the table. And we can just create an agenda and then work through that. I do foresee us splitting up into smaller working groups, possibly kind of focus working groups with particularly ADCs, maybe GPUs. But we'll see how the discussions go and then we can take it from there. So just to put it out there, I know Homan's been working on some ADCs. I've got 4 kind of topics, high-level topics: ADCs, Alveos, GPUs, and custom hardware. Anything else that people want to put on the agenda, and any kind of drill downs in each of those areas that anyone would like to suggest? Please jump in.
I was going to ask, even though I should probably know the answer to this, but are we allowed to use the breakout rooms?
Yeah, that's what I thought we were going to do. That's why I clarified with Catherine. But
okay,
yes,
cool.
Well, yes, we can use breakout rooms if you want. That's up to you.
No talks going on, so
I'll need to check how that will work.
Let's just carry on using this room. That's
Yep.
Great.
If you would like to use the breakout rooms, just let me know. I can set those up for you.
Okay, thanks, Ryan. I'll give you a shot if we do. Okay, let me share my screen. Okay, so I'm just going to be taking taking notes here. Okay, ADCs, guys. I know a lot of people are moving to custom off-the-shelf boards. We kind of used to have roaches and SWRDS where you'd have designs, you'd have ADCs that people would create on the side and interface with existing hardware. I know a lot of people have gone to off-the-shelf boards with RFSoC and the likes. What kind of ADCs are people looking at? Interested in Casperizing? Interested in designing? Anything there, guys?
This is where we could use Jonathan Weintraub's ADC list.
Yeah. Lincoln? Yes, I was just about to ask Lincoln. Please do.
Only because it's iconoclastic with everyone going to especially fast ADCs or ones with huge numbers of inputs, I thought I'd mention that we have an effort going in collaboration with Trends Electronics to introduce a board that has only 2 channels at 250 megasamples per second, 12 bits. It's intended to be something that you could use to serve at antenna digitization for an LWA type station. The TI ADS 41B29. Now we're gonna magically appear. I can say it again. ADS.
Sorry, start again.
Sure, it's an ADS 41B as in boy, 29, and there are different flavors of that. This one's from Texas Instruments. They have a 49. They have it without the B, etc. But it's they're all effectively that same thing. 2 channels up to 256 megabits per second, 12 or 16 bits. And interestingly, they also have in their data for the chip a discussion of sampling in higher order Nyquist zones. So they fully expect these chips to be used for that. And I just thought I'd add that in. It's not something we'd have to go blind into, but it's obviously easy to get faster chips.
So Lincoln, are you having a board designed? Is it designed?
Yeah, so Trends is for some reason being really nice to us. They're not charging NRE cost.
Wow.
So they're doing the development with the promise that it'll all be open IP at the end of the process.
Oh, that's wow. That's really, really kind of it. And then
still waiting to see whether it's a where this utopian vision can go wrong.
Yeah, something's coming. There's a caveat. What is the interface to this? Is this a standalone board with an Ethernet interface? Is this interfacing to an existing board?
Right. Sorry, I should have said there's a Kintex 7 on there, and in the interest of it running on minimum power, it's a 70T.
Cool.
It'll have 10 gig ports, 1 gig ports, and because of Trends' preference, there's an onboard system in package chip which provides CPU at some couple watts.
Okay.
Our goal is about 10 watts for the whole board, if we're lucky. Jack Hickish also knows about it.
Okay, great. Thanks, Lincoln.
Oh, thanks for asking.
I can say a few words about the board that we're thinking about, but haven't yet really started on. We need to digitize 500 signals for our panel SETI project, and we're thinking about a board. This is in block diagram. We haven't started laying it out yet. It'll have 16 inputs at 1.25 or 8 inputs at 2.5, or that should be 1.25, by the way, up above, and 8 inputs at 2.5 or 4 inputs at 5 gig. And we were planning to use a Kintex 7, but we're probably going to switch to the K26 SOM.
Cool. Anyone else thinking of developing ADCs, wanting ADCs?
Dan, is the K26 going to have enough output capacity?
Well, it has a single 40 gigabit port. Well, it has 4 times 12.5 gigs, and then it has a bunch of 6 gig. But that turns out to be fine for our application. It's not particularly good for other Casper users who would probably like more bandwidth. So unfortunately, I don't know of a really cheap chip that has a lot more SWRDS on it. But if you know of something that's, of order $200, we'd like to use that. Because it's fine for us to use that, but maybe not so good for other Casperites.
Wesley, I guess in the context of completeness, we should list the recent Intel announcement. I don't think those are anywhere near available, but there's a whole bunch of different ADC FPGA combinations that they announced.
Can you send around a link to that, Francois? I haven't seen anything. Is there more information about that 56 gig, or was it 64 gig a sample? Besides there was a video originally.
Yeah, I think that's what's available. I think they have a closed early access program, so they're not sharing any more than that.
Okay.
Francois, is there a link to that we can put in here, or is that?
I'll try to find it again, and I'll share it with you.
Hey, Jonathan shared his table. Okay, great. Thanks, Jonathan.
And then I think, Jonathan Weintraub et al. Have developed a quad 16.38 gig board. And that's a quad, by the way. It's a pretty amazing board. And we just heard from Holman with a single 16.3 gig board.
Yeah, that's the same chip on both those boards, just
right.
One has 4.
Great. Okay, guys, thanks very much for the input there.
The link is in the chat, Wes.
Okay, great. I'll just add that here.
Jonathan, the JPL board, I think they have a 10.6 gig 12-bit off-the-shelf board. Is that Casperized?
No, it's not. But it might be. I've also been looking at one from High Tech Global that do sort of that 10 gig sample per second 12-bit board on an FMC, and we'll possibly try and Casperize that.
I hate to be nitpicky, but both those are 16.384 gig. If you really want to.
Actually, yeah, 16.384.
Or just 16. Just call them 16 is easier. Yeah, there you go.
Actually, I think it's okay to nitpick about that.
No.
Yeah. What it is that Centec chip is spec'd at 16, but we ran it up to 16.384 because that's an interesting sample rate for Event Horizon Telescope. And it actually went a little bit beyond 16.384, but it's off the datasheet performance, right? Datasheet goes to 16. In fact, the backstory is that there was a bug in the early versions of the chip that we purchased, and it was only in late fall or early winter last year that Centec respun the chip and fixed this timing bug in the PRBS generator, and got the chip to run faster than 15. So anyway, ASNT 7123. Make sure you get the respun version, and it's a pretty decent chip for price performance, about $2,600 a piece list.
Great, thanks, Jonathan.
Just for
Dan,
your
jump
notes,
in.
you might want to make a distinction between those top 3 items, which are sort of things that people are thinking about and working on, and the bottom 2 items, which are existing and Casperized.
Well, yeah, okay, cool. I'll clear that up now.
Well, you can do it later. I don't.
Yeah, thanks, Dan. I'll make a note when I update this. Okay. Anything else on ADCs before we move on to Alveos? Okay.
Just this is Lincoln. Just one minor thing.
Yeah, Lincoln, jump in.
The manufacturer for the top one is TRENZ.
Great, thanks. Trends. Okay. So in terms of the Alveos, obviously we at the SWRDS are currently working on the U280 as well as the U50. We're also looking at using the U55C, which is still under development and I think supposed to be released second half of the year or third quarter, if I'm not mistaken. So those are the boards we're looking at, and we're looking at Casperizing. Mitch has, we had a quick chat earlier, but we'll have a look at how we go about Casperizing those boards again. But are there any other Alveos that people are interested in using and or have been using or have looked at Casperizing? I know Amit Bansod has also been playing with these boards. Anyone else? Okay, so we kind of team alone there. Amish, did you unmute there?
I've got a quick question, Wes.
Dave, yeah.
Dave.
Who's that, Dave?
Yeah. Are
Yeah,
any of those Alveos capable of PCIe 4?
No. I don't know about the U55C, but the U50 and the U280 are still Gen 3 by 16. So yeah, that's where we're at. I don't know. Maybe Patrick can actually. Is Patrick still around?
Might be. Sorry, guys. Yes, I'm still here. In fact, I might actually invoke Hugo or Cathal there because they tend to do better on these questions than I do. Hugo and Cathal.
This is Cathal here, so I've been answering some of the questions on the chat. So
You've been doing great.
Xilinx,
Thanks.
Part of Patrick's team. Yeah, I was just going to add that the PCIe support is soft, so it's part of the shell for the U280. So it's a question of whether there's a Xilinx shell, assuming you're using the Vitus flow, or whether you wanted to really roll your own PCIe Gen 4 support. I guess the question is what you're looking for. So the Gen 4 support would be ×8, and the current Gen 3 support is ×16. So it's effectively the same bandwidth. So it's, you know, you'll get a smaller interface, but it's the same bandwidth.
Okay, thanks for clearing that up.
We could check. So I believe the current shells are Gen 3 ×16. If you're interested in Gen 4 ×8, we can check what's in the roadmap and try and get back to you on that if that's of interest. Or look, on any of these questions, if you'd like to follow up, I've put my email in the chat to a couple of people privately. But if you want to email xup@Xilinx, so Xilinx University Program @Xilinx.com, we can try to follow up on any maybe outstanding questions.
And maybe if it's helpful, it pertains more to the previous section on the ADCs. But I pinged Dan privately there a moment ago. We do have plans for another RFSoC board. I'm not able to share all of those plans with the group today, but I can give Dan a heads up probably privately, which I will do. One other thing we're trying to do as part of that process, you know, we're making it open source, but in the event that you wanted to do a custom version of the board that we've done, we're trying to make sure that the vendor we're working with will enable that for you. So you know, if you came back and said, well, love the board, but you know, I need an extra port on the FPGA outside, that would actually be possible. The design itself would be open source, the Gerbers would be open source, everything, and the vendor would be willing to work with you. So that's something we've learned over the years, and we hope to be able to bring back in the next 6 to 9 months.
Are the U200s useful in the tool flow, or are they just not the right?
We never went for them because they didn't have HBM. We're looking for a board with HBM, and the U280 and the U50 both have, I think, 8 gigs of HBM. So that's why we haven't looked at the 200s.
One advantage of all of these Alveos is they have a Kubernetes device manager plugin. And so you can orchestrate these and federate these to containers and namespaces, which very soon you'll be able to composite these from multiple platforms into larger collections.
Wow, that's very cool. I didn't know that.
Okay, so that's actually, that's quite interesting. One of the things we're looking at doing is scaling these, and something like PYNQ, it's not quite scalable if you're running a host on each, or server on each board. Obviously, there's no MPSoC on these boards, but yeah, so that is something that we, I guess, currently do with Casper FPGA and what we call Core 2, our correlator management software, at least at Soraya. So that is something of interest. If you don't mind, can you maybe find a link to that? Share some info on the Slack channels.
Sure.
Thanks.
There's also, just as a point, PYNQ runs on the Alveo cards. It runs as an installable entity rather than the base server, so it's running on an Ubuntu system. And the intention going forward is that will actually be runnable in a container as well. So, and with the Ubuntu for the SOM coming, the same capability will be ported to that.
So you're saying that'll run on the host machine and interface via the PCIe?
Yeah. So in the case, we currently have PYNQ running on the 86, talking to the Alveo cards like the 280s and stuff like that.
Nice. Okay. And how does it scale across multiple servers?
Honestly, haven't addressed it at this point in time, but the next step would be to containerize, and that's how we would hope to achieve that.
Okay.
So we've done a lot of work on the containerization. We've got all the Xilinx and MATLAB tools in Jupyter Hub desktop. So
okay.
Get right to a desktop from inside your Jupyter Hub and have both interfaces.
And John, Jupyter Hub is something that we've been looking at also. We'd very much like to give access to Xilinx equipped hardware with authenticated multi-user front ends.
And if you use a couple other open source device manager plugins for Kubernetes, you can expose your JTAG serial ports, USB, I2C, you name it. You can plumb it into the container and manage the security and access through namespaces still. And
wow, you're ahead of us. Okay, cool. John, could we loop back with you separately with the big guys?
I think quite a few of us would want to chat to John. John, are you presenting it all on this?
Yeah, Wednesday.
Okay,
great.
That sounds awesome. I'll definitely be there. Okay. Anything else on the Alveos before we move on to, let's go into RFSoC next.
I was just going to ask on Alveos. I didn't see anyone from UK Research Institute on here, Matt Roberts and or Sam Bolton, but I can't remember what boards they were developing on.
I'm not sure offhand, but they are also using, so Amit Bansod from Max Planck, as well as RL, Matt and Sam are definitely using these boards. Matt and Sam and the team have developed a great 100-gig core that we are actually we're stealing or borrowing or sharing. So yeah, they've done some great work there and actually documented it really well. So we're going to be looking at yellow blocking that and getting it into the Casper toolflow. Great.
Wesley, I can hear you fine, but you're a little quieter than everybody else. Is it?
Okay.
Can you get closer to the mic or speak louder?
Okay. Is that any better?
Yeah, that's much better.
Okay, great. I'll hold the mic up. Thanks, Dan. Guys, there's been a lot of talk about RFSoC. I know Mitch is unavailable at the moment. He's had to head off. But anybody interested in other RFSoC boards as opposed to the ones that Mitch?
I can just regurgitate the ones that Mitch were talking about. It was, let's see, there's the the ZCU111, obviously, the very first one, and then there's the ZCU208 and 216 that Mitch is porting, and then there are the HTG. Oh, does anybody know the number of those? There's the Gen 5. They're the same part number, though, I think. Jack, do you remember those? You're using those boards.
There's a ZRF16 and a ZRF8, which are the 8 and 16 channel boards.
I think those are the boards that Mitch has ported or are already ported.
Okay. Yeah, Mitch has done some phenomenal work there. I don't know how he does it with kids as well. But
oh wait, I'm sorry, I forgot to mention
yeah.
the one that Patrick talked about. That's the RFSoC 2x2, 2x2.
Has that been ported or?
No, but we loaned Mitch our board, and he's so quick. You know, it'll just wait another week, or by the time we finish this meeting.
So I'll put you Mitch will port.
Dan, if it would help, we could offer Mitch a board.
He would enjoy that, but yeah, I don't think he's got our board. You already sent us one. We're happy. So
okay,
it's not urgent. We'll get ours back when he's done porting.
Great, thanks, Dan. Is anyone interested in other RFSoC boards besides the ones we've listed here? No, cool. Okay, GPUs. I know we haven't had any presentations or many presentations about specific GPU hardware yet. But
oh, I'm sorry, Wes.
Dan,
there's
are you struggling to hear me, Dan?
One little typo under RFSoC. It should be ZCU208 instead of not VVU. There you go.
Thanks. Cool. Okay, so the GPUs. I know we haven't had all the GPU presentations, and GPUs are becoming more and more prevalent every Casper workshop we have. So I just want to get a list of what GPUs people are using. I know there's a whole lot of pipelining, and there will probably be some pipelining talks at a later stage as well. But what hardware are you guys using on the for GPUs, and what hardware do you plan to use coming up in the future?
Mitch, also besides GPUs, it might be useful to have another category of FPGA boards that are not UltraScale or Alveo. You know, just
okay.
You know, like just for completeness, I think people have ported what are they? The VCU118 and the VCU128. I know people are working with those boards.
VCU118, and there was the VC. It was the VCU, right, Jeff?
I think it's the same thing, but 128, yeah.
Yeah, 128.
I don't know of any other boards, but
yeah,
I
think, if I'm not mistaken, we did some work on the 118, but we haven't actually taken it any further or used it anywhere. Okay, then any other FPGA boards that people are working on besides those two? Cool. Okay. Onto the GPUs then.
Actually, we are working on the SN1000, but for different reasons. For the networking side, that might be interest to a subset.
But is that Casper porting? Are you?
No,
John?
no. This is for networking side. It's a SmartNIC from Xilinx.
Okay, so I'm actually going to create another topic here then. It does fall under hardware, so we will look at
networking is good because we can talk about NICs and switches too.
Correct. Yeah. Okay.
Offloading.
So yeah, on the GPU front, is Tyrone still around? Or James Smith.
Yeah, I'm around. Wes, is there merit to listing specific GPU models?
I think
because they are fairly like. I mean, it's software, so what you run on the one will run on the other. I don't know that we have enough experience yet to say like what is the bar
Okay.
For
I think what is maybe worth mentioning, I mean, James has got it sort of right there, but I think what is worth mentioning is we are interested in using the tensor cores on NVIDIA GPUs, but I don't think it's worth giving you any model, but in particular.
Okay. Okay.
Tyrone
Okay,
makes
Tyrone
makes a good point.
It's
Sorry,
not kind of like FPGAs where if we ported a board, it makes it so much easier to use, I guess. So listing what GPUs people are using is kind of superfluous.
Well, there are cases where you can virtualize, like the A10 series. It's a single width GPU that could be sliced into multiple GPUs. So if you have workflows that can take advantage, you could provide more user streams from a single device. And so that's what we use these sliceable GPUs for.
Wow.
I remember NVIDIA pitched that to us a little while ago, and I wasn't sure what I was allowed to talk about and what I wasn't, just because of the whole NDA thing. But those are, I mean, that sounds very nice, John, but they are ridiculously expensive compared with the normal consumer stuff.
Yes, but when you can take an A10 and slice it up 10 times, the A10 is fairly inexpensive. It becomes
all things considered. Yeah.
But
I think for dedicated instruments, I think slicing up a GPU is not so useful, though. I think if you're virtualizing it in the cloud and you want to have multiple VMs running and that sort of thing, but for a dedicated instrument, I don't know that it's so helpful.
Yeah, I mean, the issue that we've come across mostly with our GPUs is that we're not compute bound at all. It's getting the data on and off fast enough, because they're so stupidly quick, these GPUs, that if you slice an A10 10 ways, then you've got effectively 1.6 PCIe lanes each, which, I mean, I suppose this depends on your application and exactly what you're doing. But yeah, for our purposes, I mean, yeah.
I think, as I think everybody on this thing knows, that the GPUs have a big problem getting the data in. There's a lot of computing power, they do floating point, but the Bluefield GPUs are going to have a pair of 100 gig ports directly on the board. The boards that are available now they just have a pair of the 100 gig ports, but they don't have the GPU on the board. But they're planning to add a fairly powerful GPU chip on the board as well. But right now, the only reason to use them just as a NIC. That's all they do. They're just a pair of 100 gig ports that go to PCIe 5. But I think the Bluefield will be quite interesting when it has the GPU on the board.
You can do NVMe direct offloading from the NIC to the GPUs with these Bluefields also.
Yeah, but then you might as well just use somebody else's NIC that's cheaper. But yeah, you're right.
You do have ARM cores on there too, so you can run. It has Docker running on the NIC, and so you can orchestrate containers to the NIC, which means you can do federation and workflow management. So there's a whole bunch of reasons that this integrates nicely into the Kubernetes stack with FPGAs.
So basically,
you're more than 10 minutes for your presentation.
John, it sounds as though the server is just a glorified power supply at that point.
Well, it's really close. There's another technology called Fungible, and they do PCIe disaggregation using a smart NIC and a DPU that basically will allow us to take any GPU or FPGA or any PCIe device and attach it to their high bandwidth memory on their 100 gig DPU NIC, and then attach it over to their 100 gigabit a second NIC storage brick that'll do nearly a terabit a second.
Wow.
But one of the problems, referring to Dan's comment about, we all know that ingest is an issue on the GPUs. Efficiently using that is, efficiently using the GPUs requires some sort of unified memory address system. So is that, to be across a large number of machines as well as the number of cards that you can fit in a single machine. So is that something that's looked after in what you were just
They
describing?
claim there's the ability to have coherent cache. So we're going to find out.
Yeah, theoretically with PCIe Gen 5, there's going to be something called CXL, which is supposed to solve the memory unification problem. But it's sort of a next gen thing, right? There's some sort of collaboration set up for that in like an industry working group. And I think it's all AMD, NVIDIA, Intel, et cetera, have all signed on to it. So theoretically, there will be a way of doing unified memory addressing on PCIe Gen 5, but that's not out yet. And I haven't seen a lot of details of what that's actually going to look like in practice.
Dan, there was another thing that occurred to me after you made your comments, and I'm reflecting on a discussion I had with Kate Clark. We were talking about the smart NIC with A100 processor, which NVIDIA doesn't have yet for sale really, but it's the A100E as in Edward GX. And I was asking her, so tell me really what is on this board and how wide is how many PCIe E lanes are there? Where is there a PLX, et cetera, et cetera. And by the end of the conversation, she said, they're going to be really expensive. And there's a PLX there, but there's going to be one on your server anyway. So why don't you just buy a cheaper card, which has as powerful a GPU and a really good NIC, like a Connect X6, and save your money. So her comments suggested that what seems like it would be a massive advantage in terms of direct addressing from the NIC to the GPU, even on this upcoming generation of cards, is not what we had been dreaming of.
So I think that's only true if you can do connection, if the NIC can talk to the GPU's memory space directly. If you have to go through the CPU, then you're going to run into the DDR5 limit, or the DDR4 limit, or DDR5 in next gen, which is really where I've been running into limits in all of my applications. It's DDR4 is every time I hit that before I hit even PCIe Gen 4 limitations.
Well, I think we have a whole working group about how to get data, move data around. Is that right? We have tomorrow. Is that tomorrow?
Yeah, tomorrow.
Right.
The discussion session.
Maybe we can come back to this today, but my suggestion is let's talk about, just get the hardware, get this stuff listed, and kind of postpone the discussion about high-speed data transport, if that's okay with you guys. Or leave it toward the end. Just
reasonable, Dan. It may therefore be helpful to list under GPUs, in that case, this A100 EGX card as a dream that could come true.
Yeah.
I mean, I've also seen people, or I've also seen slides from NVIDIA that imply they've thought about putting a A40 on one of these Bluefield parts, which the A40 is, that's basically the what is that? I guess the GA102 die, which is the sort of 3090 part with the GDDR memory, and that might also be. That might be a cheaper way of going about doing this if it exists, if it comes into existence.
Is anybody here using a RTX 3090?
Yes. Well, not a 3090. Yes. I use A40s because honestly, I can't get my hands on 3090.
Really I was just about to say, how did you get a 3090? Yeah. We managed to get a 3060 just recently, but
yeah. So I do know one guy who has a 3090. I have access to it, but I mostly work on A40s these days because you can actually buy them quite readily, and they're not too much more expensive than what you pay for a 3090 on eBay, honestly.
Well, I do have one node with 8 3090s that is available for experiments. And it's 100 gig connected right next to a node with U280.
Is the door to that room locked?
So is that the discontinued blower style?
Yeah.
No, this is passive.
Wow.
Wait, how did you get a passive 3090?
John is very well connected.
Okay,
well, clearly, yeah. There you go.
I need to know more. This is very interesting.
I also pasted a link to the 8 TPU ASUS card that we're plugging in. Basically, you want to have a GPU, FPGA, TPU combo in every box, and a SmartNIC. And so those are, I hear a lot of people asking about tensor cores being used out of these GPUs. Could just pure tensor cores be helpful at a very low power?
John, is this, so if I understand correctly, tensor core is the name for NVIDIA's thing for doing matrix multiply and accumulate, but that's distinct from what
more generic. This is a Google Edge TPU tensor.
Yeah, so I mean they've used the word tensor there, but is it actually the same thing?
No, I think it's a different piece of, it's not hardware compatible, not software compatible.
No, that's because I was a bit confused with that. So
yeah, the risk with having a tensor core only product for us is just the fact that we very often want to do something else with the data before or after we do our cross correlations or beamforming or FFTs or whatever it is that we like to do in this world.
Yeah, we're placing them in there just as another accelerator for doing machine learning on the network paths. We can also switch the SmartNICs that we're plugging in are for provisioning layer 2 paths anywhere on the planet over the 100 gig backbone. So we have ESNet and Internet 2 and Scenic paths at 100 gig that we can provision into these endpoints.
My guess is that those particular boards, John, are not as interesting as FPGA boards and GPU boards, but I appreciate your mentioning them. John's going to give a talk about the great stuff that he's been doing. When is your talk, John? So I recommend this talk.
Tomorrow.
Tomorrow.
10ish?
Something like 5 in the evening.
Depends on your time zone.
Of course.
Let's see, where was that? We're also going to do a little demonstration after the close. So people that want to.
Tomorrow or today?
Wednesday.
Wednesday, cool.
So 10.
I'm just, has anyone found the time of John's talk tomorrow?
I think it's 10 o'clock.
It seems to be at 10 o'clock.
17:15 European time.
Okay, great, thanks. Okay, I think, guys, I think we kind of identified everyone who is using GPUs or the guys who are the players there. If you guys want to meet up at any stage, maybe someone can organize it, just post on the Slack channel. Might be worthwhile to have a kind of targeted discussion around this and see what people are doing and what people are interested in. There was some mention of SmartNICs. John, you brought it up. What were you guys looking at? What kind of applications were you wanting to use it for?
The Bluefield 2 from Mellanox, NVIDIA, and then the SN1000 is the hot card from Xilinx.
Was it the U50 intended to be a SmartNIC originally?
Yeah, we were talking of using it as a SmartNIC, but it just seemed like a lot of work to actually get it up and running to that state. There were SmartNICs that kind of fulfilled our needs kind of natively. So, but yeah, there was talk of that there, definitely. Jonathan, what do you, sorry.
Can somebody from Xilinx say about, is the SN1000 just a better SmartNIC? Should we not try to use the U50 as a SmartNIC, or?
That's an SN1000.
SN, sorry.
Nancy.
Yeah, it's a more specialized card. I think you were referring probably to the U25, Dan, maybe?
Oh, yeah, I'm confused. You're right. Thank you, Hugo. Yeah, I was thinking about the U25. That was.
I've got an email.
Yeah. Do you know Hugo, what's the difference between an SN1000 and a U25?
I think this one has specialized chips. I can send a link also to do the compare and contrast in more specific. The other one is more fabric based. This one is actually a specialized set of chips in addition to the fabric.
And the U25, if I remember, has got a single 100 gig port and a small FPGA on it. Or maybe not so small. But.
I think it's a 25 gig. And the SN1000 is the dual 100 gig.
Right. Okay. Anyway, just for completeness, you might want to mention the U25 under SmartNIC.
Yeah, and I'll go ahead and post the link afterwards, comparing the two.
Oh, thanks.
Maybe also worth mentioning is the Bluefield 4, which has been announced at the GPU Technology Conference. It will have 700 times more compute power than Bluefield 3. But we have to wait for that, unfortunately, until 2024 or so.
Yeah, the big game changer is the NVIDIA ARM connection. They're just gonna skip over the compute and have their own compute and GPU direct connected with coherence. So
yeah, I mean, for some applications like deep learning, that's going to be a huge game changer. But I'm still a little bit unclear as to how good their interconnect with networking is going to be with regards to the sort of things that us radio correlator people like to do.
Well, they did buy Mellanox, so
they did. So yeah, it could work out well. But yeah, I need to test it.
Yeah, that's why we're actually playing around with their data center on a chip concept, and we've got one of everything, including one of their SN3700 switches for doing P4 flows and all kinds of management and shaping of traffic over wide areas.
Out of curiosity, does anybody have a Bluefield 2 yet?
I have 4 of them.
Okay. How hard are they to get a hold of? Is that like by special arrangement or?
Hen's teeth. No, I ordered them very early. I have a bad habit of as soon as I see the email from Xilinx, I push buy.
Okay, I'll have to get an order in.
Yeah.
So apologies, guys, we had some domestic at our gate. Okay, so sorry, I haven't been able to take notes here. I've missed a bit. So was that kind of wrapping up the SmartNICs?
I think Dan mentioned to also put the U25 and then we'll send something.
Say that again. Sorry, I missed it.
U25.
U25?
Yeah.
I guess
it's an Alveo board, but it should go under SmartNIC because that's really what it's meant to do.
Yeah. And we're focused on the SN1000, but I'll send the link for you guys.
Okay, thanks.
One more is the fungible S1 DPU.
Like that?
Fungible.
DPU, cool.
Yeah, GIBLE. The last few things that were discussed, I'm back on my phone now because I couldn't see. Was that John Romain speaking? But on the sort of NVIDIA Mellanox front, I dropped a message in the workshop Slack. Is that there's 2 speakers from NVIDIA Mellanox, NVIDIA Networking, speaking tomorrow. First talk is hopefully around DPU and Bluefield, and the second talk will most likely be around sort of high-speed interconnect and maybe more implementation based. So whatever questions we have outstanding now, who knows, maybe John might be able to school some of the employees as well. But I think it's good that we're having the discussion without the industry reps themselves around now. So yeah, like Dan also alluded to, tomorrow's discussion, like end of day discussion, is also going to be around this backend kind of GPU based pipelines.
Cool, thanks Mitch. Okay, so let's move on from the SmartNICs. onto custom hardware. I know in the past we've done a lot of FPGA development, or developed a lot of FPGA boards. Is anyone working on FPGA hardware or other custom hardware for their systems?
I think there are the two boards that you have under ADCs. They obviously have FPGAs on them.
Yeah, sure. I could reference back to that. Francois, did you want to jump in?
Yeah, just to say that we're also doing digitizer work. So that may or may not be RFSoC type devices, but at this stage, not.
Oh, should that be maybe listed up at the top under ADCs, or I don't know, these boards that are listed under ADCs are FPGA and ADC boards. I don't know.
Yeah, there is
a big consistent. We should just put that up there.
Yeah, I think what's starting to happen is that the custom hardware generally includes ADCs.
I think, you know, just to remind, I think a lot of you know this, but the original vision of Casper was that there would, these digitizer boards would just, it would have little tiny FPGAs on it that would just be used to packetize data. So when we talk about, I guess digitizers are not just ADC boards, they're ADC boards with FPGAs on.
That's one reason that our board only has a 70T on it, because it'll just deliver time series off the ADC. And no greedy astronomers who want other things like TFPs are allowed in the project.
Once you put an FPGA on the board, though, then it's like, you know, hard to resist putting more functionality on too.
Right.
But you still got
that was the
20%
big
space.
mistake we made with the iBob. We used an oversized FPGA, and people figured out you could do more than digitizing and packetizing.
Okay, then let's move on to networking hardware. There's probably a lot of stuff out here. A lot of people are moving on to 100 gig. What are you guys using? What hardware? What are you interested in?
So 40 gig is like the common thing these days, and 100 gig is kind of coming up, but it's still pretty expensive to deploy in mass quantities.
Okay, so are most people actually still using 40 for their instruments then? I know our work going forward will be 100 gig.
Yeah, if I could just sort of interject, it seems as though the vendors would really rather that you don't buy 40 gig stuff at this stage, because they don't really want to sell it to you anymore. If you're plundering eBay for your radio astronomy purposes, then there's lots of 40 gig stuff kicking around, and it's very affordable. Once you get up to sort of 200 or 400 gig, then stuff starts to get expensive, but it is actually quite readily available from what I've found.
Yeah, I would echo that. I have a lot of 40 gig instruments, and I'm having a hard time sourcing parts for various 40 gig components, whereas 100 gig now is so easy to come by that I'm trying to transition as much as I can to 100 gig.
Most 100 gig stuff, I mean, specifically NICs, you can kind of set them to work at 40 gig. Granted that we basically a Mellanox only house at Soreo, so our stuff all kind of works. So that, yeah, the 100 gig and the 40 gig can interconnect.
Yeah, and like even the E810 cards from Intel can do 10 gig still. So if you have like old 10 gig stuff, I found it super useful to do like 8 by 10 gig connections off of those cards.
Sorry, how do you do 8 by 10 gigs off?
Well, it's off of 2 QSFPs. Well, I guess it's their QSFP DDs, but you're backwards compatible. Like you're putting them backwards compatible to QSFP plus. And then QSFP Plus can break out to 4 10 gig lines.
Okay. That makes sense, yeah.
And the E810 seem to work. Well, I have one on order, but it looks like it's going to make it my life a bunch easier for interoperating with old FPGAs.
Yeah, I think kind of, I know Tyrone can probably comment more on this, but we might be we're looking at some stage of doing some hybrid 40 gig, 100 gig systems. particularly while there's a bit of a changeover. But yeah,
so Wes, if I can just comment there, and James will probably add to it. So initially we wanted to try and run our existing 40 gig, or rather replace some of the switches in our existing 40 gig network with 100 gig switches, but there are some interoperability challenges with the PIM bidirectional implementation that we use for our application, which is why we have to just roll out a new network entirely. But we are looking at some sort of switching mechanism to at least let the incoming antenna data be streamed to both 40 gig and 100 gig networks for our new system.
Is it simultaneously, or do you flip a switch?
We're hoping it's going to be simultaneously. That's the intention, at least.
It's simultaneously. Tyrone's basically captured it there. It's not hard to share.
The 100 gig switches that we have, I think, and maybe everybody else's switch can do. They can become 40 gig ports or 4x10 gig E ports.
So Dan, the issue that Tyrone was highlighting that we came across was it's just the different Mellanox have sort of end of life their old SwitchX chips or ASICs, and their new one is called Spectrum with a new operating system and all these kinds of things and protocol stacks. And in our labs, we have a new switch and an old switch, and we try to get them to talk to each other. On all the normal, i.e. unicast protocols, they work. So OSPF works, and they can route and they can talk to each other. That's just fine. But I'm actually not sure how general this is in Casper. We're using PIM bidirectional multicast to get our data around, and the SwitchX and the Spectrum just don't talk to each other in that case. We haven't really explored any other vendors, so I'm not sure if the problem is more general. We've reported it to Mellanox, and they have kind of reproduced the problem, but they've indicated that they're not terribly interested in fixing it at this stage, since our switches are basically out of support. The solution Tyrone was talking about was we basically used some L2 switches as splitters, so to speak. With IGMP snooping, so the multicast works, but then you just use an ACL to block the two networks from talking to each other. So the data flows from the digitizers and it gets multicasted to both of the networks, and then they are kind of operated on it independently. So that's how we'll be building our prototype GPU correlator in any case, using the same data as the old one is doing.
We are using Arista, and we don't configure it that way, so I can't really tell you if our stuff works or not.
The change that Mellanox is moving towards QSFP56 is also confusing a lot of the interconnects. So I pasted a link in both the chats for Credo. They make an electrically active cable that can transcode from one to the other. And so we're actually testing this on the blue field, which is 100 gigabit QSFP 56, splitting it out to two 100 gig 28s. And we're going to try that out in a Juniper to see if it works.
Ooh, it's purple.
So that's the other, like the switches have no problem, well, some problem accepting non-standard optics. For the Mellanox 3700, we are running the Sonic OS, and we had to get a special firmware to enable the non-standard optics so we could talk back to our other system. But yeah, a little hammering, it works. But the Credo cables are pretty interesting.
What are you using on your? Are you multicasting on your network, John? Because I wasn't able to get any multicast working on Sonic.
Really interesting. That's one of the things that I am interested in trying out.
Granted, I had only about a week to play with this, and I was trying to figure out a lot of things at the time. And I wasn't using it on a Mellanox switch. I was using it on a actually, no, it was a Mellanox switch. It was the 3800, which they said, yeah, that doesn't work anymore, and they took it back from us. And I haven't played with it since. But we can maybe talk about that another time.
Yeah, so they have a whole new it's containerized operating system build Docker. And so they actually have Kubernetes built into it now. So you can actually join your switch to your Kubernetes cluster. Imagine the possibilities.
Imagine the headaches.
No.
Okay, guys. So I think it might be worthwhile for you guys just to meet together as well and have a chat about networking. I think there's a lot more to discuss here. But I think if there's nothing else, I would like to wrap this up. So quickly, last comments or thoughts before we call it a day. Okay, let's do it.
Wesley,
Guys,
just a quick question. If there are people who are interested in digging deeper into some of these things, then you should probably just connect, and maybe we'll leave this open. So use the chat to do that. If there was any subgroups forming.
Yeah, so there's this chat. Okay, let's leave this open. If Ryan's happy to do that.
Yeah. So this Zoom is going to last till 6 p.m. So you have about another 6 hours, which I assume would be enough time.
Should be enough.
I don't think I have another 6 hours. I'm probably going to drop off.
Yeah, that's why I'm hoping. That's why I gave about 6 hours, hoping that that'd probably be more than enough time for people to discuss. If people would like, I can create breakout rooms before you kind of all sign off of the main.
I think, does everyone have the ability to create breakout rooms, or is it just the host?
No, just the host and co-host.
Just the host.
Once the breakout rooms are created, people can freely join in and out.
Okay. So then maybe let's say, James, would you guys like to continue this network discussion?
I would, but I would also like to go to bed. So I don't know if it's possible. Maybe at another time.
Okay, then maybe let's do it.
We do have a working group on high-speed data transport. So but that unfortunately is also kind of the same general time as this working group, on a different day, obviously. It'll be an hour earlier.
What day is that? I'm looking.
I think that might be part of tomorrow's, as it's called, backend pipeline discussion. But that being said, there is a free session open on the final day on Thursday, if I'm not mistaken. So that could also happen there. Any other LLC members want to chime in there?
I don't think there's still a free session on Thursday, but that day was going to finish a little earlier, so we could add a session. But we could also try to make the Zoom room available on a different day, so that it doesn't just get added later and later.
Okay, that's fine. I mean, I'm happy to fall in with whatever the plan is.
If it's just 2 or 3 people, it might be best if those 2 or 3 people, work offline to figure out the best time slot, depending on what countries they're in or something, and schedule their own Zoom. But for larger things, we should try to set something up for them, I guess, maybe on Friday or something.
Yeah, that also works. So John, I can probably I'll reach out to you on Slack, and we can take this sort of online, offline.
So I think, James, when you do that, also just maybe post it onto the Slack community.
The workshop Slack.
See who else is interested, and let them know what time you guys are meeting.
Will do. I'll carry on with that tomorrow.
Maybe what you guys could do is see how much time we have for this kind of discussion as a larger group tomorrow, when we have a little bit of time to discuss it. And then if we don't get to the kind of nerdy stuff that you guys want to get into, you guys can work to schedule another little session and invite who you want.
Okay, that works. Works for me.
Great. Well, thanks, guys. Thanks to the committee, the organizing committee. You guys have done a phenomenal job. Catherine, thank you.
Hey, Catherine, do we have a little time when Wes can present the results of the working group and other groups can? Is that for Thursday? Do we have?
We can do that. so I think Amish was going to give a closing summary talk, but maybe it would be good to have breakout
The
discussion leaders
individual.
give a short, either give a short summary or contribute information to Amish's summary. Amish, do you have a preference for how that would work?
No, not really. I had a similar question from Matthews earlier this South African day. The thing is, I think previously we've done it where sort of 10 to 15 minutes before the actual day start, like the next day start, we had a quick feedback session on previous evening's discussion, which is cool because it's still sort of fresh in everyone's memory. But I'm also down to do a sort of more overall altogether feedback on Thursday on the final session. I think maybe specifically in this case, considering the talks lined up for tomorrow, it might be good to feedback just a 5 minute or so.
That sounds good.
Do we have any canceled talks, Catherine? Are there any empty slots?
Not at the
Okay.
moment. But I'll figure out. I'll figure out.
Guys, I think we've literally had the majority of the attendees here on this call, so most people have already heard this. So it's not like this is a breakout.
Yeah,
people,
that's
only
right.
10 people.
We're at
So
40
I don't know if we
people.
actually need to feedback. Most
That's
people
true.
have heard this.
Yeah, maybe that's a good point. Maybe we don't have to give a feedback. Maybe we could just give it as a written feedback to the people
Sure.
that could
Yeah.
attend.
Yeah.
That
Okay.
sounds good.
Thanks, guys. We'll
Awesome.
see you all tomorrow.
See you.
Thanks, everyone.
All right, thanks,
Cheers.
ladies and gents.
Thanks all. Cheers.
Bye.
Cheers. Bye bye.
Thanks. Bye.